Before we touch any tools, code, or platforms, we need to reset how we think about AI. Most confusion around AI doesn't come from complexity, it comes from missing mental models. People jump straight into tools without understanding how AI systems actually work underneath. Today is about building that foundation. If you understand the structure of AI systems, how inputs, models, logic, and feedback fit together, you'll be able to learn any tool, any framework, and any model that comes next. Day one is not about doing more, it's about thinking clearly. Everything we build in the next 13 days will rely on what you learn today. Today, we're moving away from buzzwords and toward clarity. AI is often presented as something magical or abstract, but in practice, it's a system made of very concrete parts. Tools may change, but systems don't. The goal of day one is to help you think like an AI system designer. That means understanding how the pieces fit together, what role each piece plays, and where problems usually arise. If you can explain how an AI system works on paper, you can eventually build it in code. That's the mindset we're developing today. AI feels confusing because the conversation around it is messy. Terms like AI, machine learning, and large language models are often used interchangeably, even though they mean different things. On top of that, tools hide complexity behind simple interfaces. When you use AI through a chat box, it feels like the system is doing everything on its own. But that's an illusion. Without understanding what's happening behind the scenes, people struggle to move from usage to creation. Today, we're removing that confusion by separating concepts and showing how they connect. At the highest level, AI refers to systems that perform tasks that normally require human intelligence. This includes understanding language, recognizing patterns, making decisions, or generating content. The key thing to remember is that AI is a capability, not a single technology. There are many ways to build AI systems, and large language models are just one of them. When people say AI, they're often referring to the outcome, not the mechanism. Keeping that distinction clear will help you reason about systems more effectively. Machine learning is one approach to building AI systems. AI is the goal, machine learning is a method. Instead of writing explicit rules, we train models to learn patterns from data. Not all AI systems use machine learning, but most modern ones do. This distinction matters because it helps you understand what problems are best solved with learning versus logic. When you're designing AI systems, you're often deciding how much intelligence comes from data-driven models and how much comes from traditional software logic. Large language models, or LLMs, are a specific type of machine learning model. They're trained on massive amounts of text and learn to predict what comes next based on context. That's it. They don't understand in a human sense, and they don't know your goals. They're powerful pattern generators. In real applications, LLMs are components inside larger systems. Treating them as complete solutions leads to fragile designs. Treating them as tools inside a system leads to reliable ones. Chat interfaces make AI feel simple, but they hide critical details. You don't see how data is prepared, how prompts are structured, how outputs are validated, or how errors are handled. In production systems, these hidden steps are where most of the work happens. If you only learn AI through chat tools, you miss the system thinking required to build real applications. Today, we're intentionally stepping behind the interface to see the full picture. Chat interfaces make AI feel simple, but they hide critical details. You don't see how data is prepared, how prompts are structured, how outputs are validated, or how errors are handled. In production systems, these hidden steps are where most of the work happens. If you only learn AI through chat tools, you miss the system thinking required to build real applications. Today, we're intentionally stepping behind the interface to see the full picture. The simplest way to think about an AI system is as a loop: input, processing, model, output, and feedback. This loop is universal. The complexity comes from how each part is implemented, not from the structure itself. If something goes wrong in an AI system, the issue almost always lives in one of these stages. This loop will be your debugging and design tool throughout the course. Inputs are everything the system receives. This could be user text, uploaded files, images, audio, database records, or events from other systems. Quality matters here. Poor inputs lead to poor outputs, no matter how good the model is. Designing good AI systems starts with understanding what information the system needs and how it should be formatted. Input design is one of the most overlooked skills in AI development. Processing is where most of the real work happens. This includes cleaning data, structuring prompts, applying rules, enforcing constraints, and routing logic. Models are powerful, but they're also unpredictable. Processing steps give you control. When AI systems fail in production, it's often because processing was rushed or ignored. Learning to design this layer well is what separates experiments from real systems. The model is the component that performs the intelligent task: language generation, classification, recommendation, or perception. Models don't know your business goals, your users, or your constraints. They simply produce outputs based on inputs. It's your responsibility as the system designer to use them correctly. Models are powerful, but they're never autonomous on their own. Outputs are what the system delivers: text, structured data, decisions, or actions. In real systems, outputs must be usable. That often means structured formats, predictable behavior, and validation. A beautiful response that can't be consumed by software or trusted by users is not a good output. Output design is just as important as model choice. Feedback closes the loop. This could be user corrections, human review, logs, metrics, or retraining data. Without feedback, systems don't improve, they just repeat mistakes. Feedback mechanisms are what turn AI from a static tool into a learning system. Even simple feedback signals can dramatically improve reliability over time. Let's ground this in a real example. An AI resume screener takes resumes and job descriptions as input. It processes and normalizes the text, applies a matching model, and outputs ranked candidates. Feedback comes from recruiter decisions: who gets interviewed or rejected. This same system loop applies across industries. The domain changes, but the structure stays the same. Tools, APIs, and models will change quickly. What won't change is how AI systems are designed. If you understand this system level view, you're never locked into a single tool or vendor. You gain the ability to adapt. This is the difference between someone who follows tutorials and someone who builds products. Today's lab is intentionally simple. No code, no tools, just thinking clearly. You'll choose a real-world problem and map it into the system loop: inputs, processing, model, outputs, and feedback. This exercise forces clarity. If you can't explain the system on one page, you can't build it reliably in code. Your deliverable is a one-page AI system blueprint. This can be a diagram or a structured outline, written in Markdown or exported as a PDF. This blueprint will become the foundation for future builds. As the course progresses, you'll come back to this document and turn ideas into implementation. This is your first step toward thinking like an AI architect. Tomorrow, we move from thinking to building. You'll take these mental models and turn them into a working development environment. Day one makes everything else easier. If today clicked, the rest of the course will feel logical instead of overwhelming. AI development starts with clarity, and now you have it. Now that we've talked about how AI systems are structured, it's time to apply that thinking. This lab is intentionally low-tech and high clarity. There's no coding today because the hardest part of AI development isn't writing code. it's designing the system correctly. By the end of this lab, you should be able to take any real world problem and explain how an AI system would solve it using a simple, repeatable structure. This skill transfers across tools, models, and frameworks. If you do this step well, everything you build later becomes easier. In this lab, your goal is to translate a real world problem into an AI system design. We're not building anything yet, we're mapping it. You'll use a simple loop: input, processing, model, output, and feedback. This loop is the backbone of almost every AI application in production today. If you can clearly describe each part, you're already thinking like an AI builder. Take your time with this. Clarity here saves hours later. Start by choosing a real problem, not a vague idea. A good problem has a clear user, a specific goal, and a concrete output. Avoid broad goals like build an AI assistant. Instead, choose something focused, like detecting phishing emails or ranking resumes. The more specific the problem, the easier it is to design a system around it. Write your problem in one clear sentence before moving on. Next, define who this system is for and how you'll know it's working. Ask yourself who uses the output and what a good result looks like. Also, think about failure. What would make the output unacceptable or unsafe? Writing down success and failure criteria forces you to design intentionally. AI systems without clear success metrics tend to drift and break over time. Now list everything that enters the system. Inputs could be text, files, images, metadata, or events. Be explicit about formats and sources. For example, is the input a PDF uploaded by a user or structured data from a database? Input quality directly impacts output quality. Many AI failures come from poorly defined inputs, not weak models. Treat input design as a first-class task. Next, define exactly what the system must produce. Outputs should be clear, structured, and usable by either a human or another system. Avoid vague outputs like a helpful response. Instead, think in terms of ranked lists, scores, categories, or structured fields. If you can describe the output format precisely, you're already reducing ambiguity and increasing reliability. Now decide what role the AI model plays in your system. Is it generating text, classifying inputs, ranking options, or extracting structured data? It's just as important to define what the model does not decide. Models assist, they don't own the final decision. Clear boundaries prevent over-reliance on AI and make systems safer and easier to debug. Processing is everything that happens before and after the model. This is where most of the intelligence actually lives. Before the model, you might clean data, format inputs, or construct prompts. After the model, you validate outputs, apply rules, or handle errors. Strong processing turns unreliable AI into dependable systems. Feedback closes the loop. Decide how the system learns from outcomes. This could be user corrections, human review, or tracking real-world results. Feedback doesn't have to be complex. Even simple signals can dramatically improve performance over time. Systems without feedback don't evolve. They repeat mistakes. Always design feedback intentionally. Now bring everything together. Create a simple diagram or structured outline showing the flow from input to feedback. Keep it simple. One page is enough. The goal is clarity, not perfection. If someone else can understand your system by looking at this diagram, you've done it right. Before finalizing, stress test your system. Ask what happens when inputs are messy, the model is wrong, or users behave unexpectedly. For each risk, add at least one mitigation, either in processing or feedback. This is how professionals design resilient systems. Anticipating failure is part of building responsibly. Your final deliverable is a one-page AI system blueprint. It should include the problem statement, system flow, success criteria, and feedback mechanism. This document is more valuable than it looks. It becomes the foundation for implementation, testing, and iteration. Save it. You'll reuse this structure again and again. This lab teaches you how builders think. Tools come and go, but system design skills stay relevant. Tomorrow, you'll take this blueprint and start turning it into a working environment and code. The better this design is, the smoother everything else becomes. This is how real AI projects begin. Before we build anything intelligent, we need to become operational. Most AI projects don't fail because the models are bad. They fail because the environment is fragile. Broken installs, conflicting libraries, unclear structure, and missing version control stop progress before it starts. Today is about removing friction. By the end of day 2, you'll have a clean, repeatable AI development setup that you can reuse for every project going forward. This is not about memorizing commands. It's about understanding how professional AI work is organized so that when we start building real systems tomorrow, nothing gets in the way. Yesterday, you learned how AI systems are structured conceptually. Today, we turn that understanding into something executable. Day 2 is about making sure you're ready to build. That means having a working Python environment, isolated dependencies, a clean project structure, and version control. These may feel basic, but they are foundational. Every real AI system you build will sit on top of this setup. Think of today as preparing the ground before construction begins. Most frustration in AI development has nothing to do with AI itself. It comes from environment issues, things not installing, versions conflicting, or projects becoming unmanageable. A clean setup prevents wasted time and confusion. It also makes your work reproducible, which is essential if you ever collaborate, deploy, or revisit a project later. Professionals don't skip this step. They invest in it once and benefit every time they build. Most frustration in AI development has nothing to do with AI itself. It comes from environment issues, things not installing, versions conflicting, or projects becoming unmanageable. A clean setup prevents wasted time and confusion. It also makes your work reproducible, which is essential if you ever collaborate, deploy, or revisit a project later. Professionals don't skip this step. They invest in it once and benefit every time they build. A professional AI development environment has a few core components: Python, isolated dependencies, a clear project structure, and version control. These pieces work together. Python runs the logic. Environments keep dependencies clean. Structure keeps projects understandable, and Git tracks progress. Tools may change, but this foundation stays the same across almost every AI team and organization. Python is the default language for AI development, not because it's the fastest, but because it's flexible, readable, and supported by a massive ecosystem. Most AI libraries, APIs, and tools are designed with Python in mind. You don't need to be a Python expert to build AI systems. You need just enough to glue components together, call APIs, handle data, and manage workflows. That's what we focus on here. For AI development, Python is a tool, not the goal. You need to be comfortable running scripts, importing libraries, handling environment variables, and printing results. You're not implementing algorithms from scratch. You're orchestrating systems. Think of Python as the connective tissue that links models, data, logic, and outputs together. Simplicity and clarity matter more than clever code. Virtual environments solve a very real problem: dependency chaos. Different projects require different versions of libraries, and mixing them causes breakage. A virtual environment isolates each project so its dependencies don't interfere with others. This makes your work predictable and reproducible. If something breaks, you can rebuild the environment without touching your system or other projects. Think of a virtual environment as a sandbox. Inside the sandbox, you install exactly what your project needs: Outside of it, nothing changes. This separation is what allows professionals to work on many projects at once without conflicts. Once you adopt this habit, environment problems become rare and manageable instead of constant and frustrating. Project structure is how you communicate intent to yourself and to others. A well structured project makes it clear where logic lives, where experiments go, and how to run the system. Without structure, projects become confusing quickly. With structure, scaling becomes possible. Today, we establish a simple layout that works for small experiments and larger systems alike. A clean project layout usually separates application logic, scripts, configuration, and documentation. This separation helps you avoid mixing experiments with production code. It also makes onboarding easier if someone else looks at your project. Clear structure is a professional signal. It shows you know how to build maintainable systems. Git is non negotiable in professional development. It tracks changes, enables collaboration, and lets you recover from mistakes. In AI work, where experiments and iteration are constant, version control becomes even more important. Git gives you confidence to try things, knowing you can always go back. It also forms the basis of your public portfolio. A good repository is understandable without explanation. It includes a README, setup instructions, clear structure, and an example run. This is how others evaluate your work, whether that's teammates, hiring managers, or collaborators. If your repo is clear, your thinking usually is too. Now it's time to get operational. In today's lab, you'll set up Python, create a virtual environment, run your first AI-related script, structure the project, and push everything to GitHub. By the end of this lab, you won't just understand how AI development works, you'll be ready to do it consistently. Your first task is to ensure Python is installed and working correctly. You'll check the version and run a simple test script. This confirms that your system can execute Python reliably. Everything else depends on this step, so it's worth verifying carefully. Next, you'll create and activate a virtual environment for this project. This isolates dependencies and sets the standard for future work. From now on, every AI project gets its own environment. This habit saves enormous time and prevents subtle bugs later. Next, you'll create and activate a virtual environment for this project. This isolates dependencies and sets the standard for future work. From now on, every AI project gets its own environment. This habit saves enormous time and prevents subtle bugs later. With the environment working, you'll organize the project, create folders, move code into the right place, and add a README. Doing this early prevents chaos later. Structure is easier to establish now than to fix later. With the environment working, you'll organize the project, create folders, move code into the right place, and add a README. Doing this early prevents chaos later. Structure is easier to establish now than to fix later. Finally, you'll initialize Git, commit your work, and push it to GitHub. This turns your local setup into a real project. From this point forward, everything you build has a history and a home. This is how professional AI work is done. Today is the last day focused on plumbing. From tomorrow onward, every lesson builds directly on this setup. If day 2 is solid, the rest of the course feels smooth and logical. You are now operational and ready to build real AI systems. This lab is where everything becomes real. Up to now, we've talked about systems and structure. Today, we remove the most common blocker in AI development: environment friction. This is not about doing something impressive, it's about doing something correctly. A clean setup saves you hours later and makes every future build smoother. Go step by step, don't skip ahead, and don't worry if things feel slow at first. By the end of this lab, you'll be fully operational and ready to focus on building AI systems instead of fighting your setup. Today's lab has one clear goal: get you operational. That means your computer is ready to run AI code reliably. Your project is structured professionally, and your work is tracked in Git. We'll move from installing and verifying Python to running your first script to pushing a clean project to GitHub. Nothing here is optional in real AI work. This lab sets the foundation for every build that follows. By the end of today, you won't just feel ready, you'll have proof. You'll have Python installed and verified, a virtual environment isolating your dependencies, a script that runs successfully, and a GitHub repository with your first commit. These are concrete outcomes. If you ever feel unsure later in the course, you can come back to this setup and know that your foundation is solid. Everything starts with Python. Your first task is to install Python version 3.10 or higher and confirm it runs correctly from the terminal. This verification step is important. Many issues later come from assuming Python is set up correctly when it isn't. Once you see the version number printed, you know your system can execute Python code, and that's the base layer for everything else. Next, create a dedicated folder for this project. This folder is the home for everything you'll build during the course. One project, one folder. This keeps your work clean and prevents files from scattering across your system. Naming and structure may seem minor now, but they matter a lot once projects grow. Now you'll create a virtual environment inside your project. This isolates your project's dependencies from everything else on your machine. Think of this as a sandbox. Everything installed inside it belongs only to this project. This step prevents version conflicts and makes your setup reproducible. Always activate the environment before running or installing anything. With the virtual environment active, upgrade the package manager. This ensures you're working with the latest, most stable tooling. It's a small step, but it prevents subtle issues later, especially when installing AI libraries. This is part of building a habit of maintaining a healthy environment. Before writing more code, you'll create the project structure. This includes folders for source code, scripts, tests, and documentation, along with a README and a gitignore file. This structure keeps experiments separate from application logic and makes your project understandable to others. Professionals organize before they scale. Your .gitignore tells Git what not to track. This includes virtual environments, cache files, and secrets. Never commit environments or keys. This step protects your project and prevents mistakes that are hard to undo once code is public. Treat .gitignore as a safety net. Now you'll write your first script. Keep it simple. The goal is not intelligence, it's execution. This script proves that Python runs correctly, the environment is active, and your project structure works. We'll replace placeholders with real AI logic later. For now, success means the script runs and prints output. Run the script from the terminal and confirm it prints the expected output. This is a key moment. If the script runs, your environment is healthy. If something fails, fix it now, before moving on. Debugging setup issues early saves frustration later. Next, write a simple README. This file explains what the project is and how to run it. A good README makes your work accessible to teammates, reviewers, or your future self. Clear documentation is a professional habit, not an afterthought. Now, you'll initialize Git in the project folder, stage your files, and create your first commit. This commit captures your clean starting point. From now on, every meaningful change should be tracked. Git gives you confidence to experiment because you can always go back. Create a GitHub repository, link it to your local project, and push your code. This step turns your local setup into a real, shareable project. It also starts your AI portfolio. From here on, everything you build has a public history. When you're done, you should have a working Python environment, a virtual environment, a running script, a clean project structure, and a GitHub repo with at least one commit. If all of those are true, you're done with the lab. This lab removes friction. From tomorrow onward, your focus shifts entirely to AI logic, systems, and behavior, not setup issues. You've built the foundation once correctly. Everything that follows will build on this. This is how real AI projects start. Up to now, we've focused on thinking clearly about AI systems and making sure your environment is solid. Today is where AI becomes real in your code. This is the point where many people stop relying on chat interfaces and start building actual AI powered software. The goal today is not to memorize an API or learn a specific vendor. It's to understand the universal pattern of how large language models are accessed programmatically, how their behavior is controlled, and how cost and performance trade offs show up in real systems. Once this clicks, you can work with any modern LLM. Yesterday, you became operational. You set up Python, isolated your environment, and created a clean project repository. That groundwork is what allows today to go smoothly. Today, you will send text to a real language model through code and receive a response back. This is the foundation of almost every modern AI application. By the end of the day, you'll have a working command line AI assistant that you built yourself. Real AI products are not built in chat windows. They're built by calling models through APIs. APIs allow your code to talk to models automatically, repeatedly, and at scale. When you use an API, AI becomes a component inside a system instead of a standalone tool. This enables integration with databases, user interfaces, workflows, and other software. Learning to work with APIs is the moment AI becomes programmable rather than interactive. At a high level, an LLM API is a service that accepts structured input, runs a language model, and returns structured output. It doesn't remember past calls unless you provide context explicitly. This stateless nature is important. Every request must contain everything the model needs to respond correctly. Once you understand this, many common AI issues like why did it forget become obvious. Every API call follows the same basic pattern. Your code sends a request, the service processes it, the model generates output, and the response comes back. This is no different from calling a weather API or a payment API. The only difference is that the response is generated text. Thinking of LLMs as just another API simplifies how you design systems around them. An LLM request contains several key pieces: which model to use, the messages or prompt, parameters that control behavior, and authentication credentials. Each of these affects the output. Changing the prompt changes meaning. Changing parameters changes style. Choosing the model changes cost and capability. Professional AI development is about controlling these inputs intentionally. LLMs don't read text the way humans do. They operate on tokens, which are chunks of text. Both your input and the model's output are measured in tokens. This matters because tokens directly affect cost and performance. Longer prompts take more time and cost more money. Understanding tokens helps you design efficient systems instead of guessing why things feel slow or expensive. Temperature controls how deterministic or variable the model's responses are. A low temperature produces more predictable outputs, which is ideal for structured tasks like extraction or classification. Higher temperatures introduce variation, which can be useful for creative tasks. In production systems, lower temperatures are usually preferred because consistency is more valuable than novelty. Separating system prompts from user prompts is one of the most important reliability techniques. The system prompt defines the role, rules, and boundaries for the model. The user prompt contains the task-specific input. This separation helps prevent prompt injection, improves consistency, and makes your systems easier to reason about. It's a simple pattern with a big impact. Prompt quality is less about clever wording and more about clarity. Good prompts define the task constraints, and expected output clearly. Vague prompts produce unpredictable results. Structured prompts produce stable behavior. When AI systems fail in production, it's often because the prompt was ambiguous rather than because the model was weak. LLM usage is typically billed based on tokens. That means you pay for both what you send and what the model returns. This has design implications. Small changes in prompt length or output verbosity can have large cost effects at scale. Understanding cost early helps you build systems that are sustainable, not just impressive. Performance is mainly about latency and reliability. Larger models and longer prompts usually mean slower responses. In practice, many performance improvements come from simplifying prompts, reducing token usage, and choosing the right model for the task. Performance is not just an infrastructure problem, it's a design problem. API keys authenticate your requests and track usage. They should never be hard coded into scripts or committed to GitHub. Instead, keys should be stored in environment variables and loaded at runtime. Treat API keys like passwords. Good key hygiene is part of professional AI development, not an optional extra. In today's lab, you'll put all of this together. You'll write a Python script that sends text to an LLM API and prints the response. This may look simple, but it's a major milestone. Once you can do this reliably, you can build agents, workflows, tools, and full applications on top of it. You'll start by creating a new script and loading your API key from an environment variable. This keeps credentials secure and your code reusable. You'll also import the necessary libraries. This step sets the pattern you'll use in every future AI script. Next, you'll construct the API request and send it to the model. This includes specifying the model, providing the prompt or messages, and setting parameters like temperature. This request is the heart of the interaction. Once this works, you have direct programmatic access to an LLM. After the request completes, you'll receive a response object. Your task is to extract the generated text and display it cleanly. Handling responses correctly is just as important as sending good requests. Real systems need to parse, validate, and sometimes reject model output. Now you'll turn the script into a simple tool. You'll accept user input from the command line, send it to the model, and print the response. At this point, you have a working CLI-based AI assistant. It's simple, but it's real. By the end of day 3, you should have a Python script that accepts input, calls an LLM API, and prints output. This script should be committed to your GitHub repository. This is your first real AI application built through code. Common early mistakes include hard coding API keys, ignoring token limits, using high temperature everywhere, and mixing system instructions with user content. Avoiding these habits early will save you significant time and frustration later. From this point forward, everything you build, agents, tools, workflows, applications, depends on this skill. If you can reliably talk to models through APIs, you can build modern AI systems. Day 3 is the gateway from setup to real AI development. This lab is where AI stops being theoretical and becomes something your code can actually talk to. The goal today is not to build something complex. It's to learn the single most important interaction pattern in modern AI development: sending text to a model through an API and receiving a response back in your application. Once you understand this pattern, everything else, agents, tools, workflows, automation, is just composition on top of it. Go step by step, focus on correctness over speed, and treat this as the foundation for all future AI systems you'll build. Today's lab focuses on one outcome: calling a real language model from Python and seeing a response come back into your program. This is the moment where AI becomes programmable. You'll start with a simple script, make a secure API call, and print the model's output. By the end of this lab, you'll have a working command line AI assistant. It may look simple, but this pattern powers almost every AI product in production today. You are building the simplest possible real AI application. A user types text, your code sends that text to a model, and the model returns a response that you display. This text in, text out pattern is the core building block of AI systems. Whether you later add memory, tools, or workflows, this interaction always sits at the center. Focus on making it clean and reliable. Before writing any new code, pause and verify your setup. You should have your Day 2 project cloned locally, your virtual environment activated, and a GitHub repository connected. You'll also need an API key from an LLM provider. If any of these pieces are missing, fix them now. Most frustration later comes from skipping prerequisite checks. Always work inside the correct virtual environment. This ensures your dependencies are isolated and predictable. Navigate to your project directory, activate the virtual environment, and confirm Python runs from inside it. This step prevents subtle issues that are hard to debug later. Make this a habit you follow every time you work on an AI project. Now you'll install the libraries needed to talk to the LLM API and manage configuration. This typically includes the provider's SDK and a utility for loading environment variables. After installing, save the dependency list. This allows anyone else, or future you, to recreate the same environment. Dependencies are part of your project's contract. API keys should never appear in source code. Instead, store them in a local environment file and load them at runtime. This protects your credentials and keeps your repository safe to share publicly. If a key ever leaks, you can rotate it without changing code. Secure key handling is a professional baseline, not an advanced topic. Now you'll create the script that becomes your AI assistant. Place it in the scripts folder and give it a clear descriptive name. This script will hold all the logic for reading user input, calling the model, and printing output. Keep it focused, one responsibility per file. Before making any API calls, load your configuration. Read the API key from the environment and validate that it exists. If the key is missing, exit with a clear error message. Failing early and clearly is better than producing confusing errors later. Configuration checks are part of building reliable systems. Now define how you talk to the model. Separate system instructions from user input. The system prompt sets behavior and constraints, while the user prompt carries the actual question or task. This separation improves consistency and safety. It also makes your prompts easier to reason about and modify later. This is the core step. Construct the API request, choose a model, and set parameters like temperature and token limits. Send the request and wait for the response. At this point, your code is talking directly to a language model. Everything else you build in this course will reuse this exact interaction pattern. The API returns a structured response. Your job is to extract the generated text cleanly and present it to the user. Do not assume the response is always perfect. In real systems, this is where validation and error handling live. For now, focus on clean extraction and readable output. Next, turn the script into an interactive tool. Prompt the user for input, send it to the model, and display the response. Add a simple exit command so the user can quit cleanly. With this loop in place, you now have a usable command line AI assistant. Run the script from the terminal and test it with a few prompts. Confirm that input goes in and output comes back consistently. If something fails, debug it now. Most issues are configuration related. Fixing them early keeps momentum high. Now, document what you've built. Update the README to explain how to set up the environment, add the API key, and run the script. Good documentation turns a script into a project. Assume someone else will read this without context and still be able to run it. Commit your changes and push them to GitHub. This records your progress and makes the work real. From here on, every meaningful change should be committed. Version control gives you confidence to experiment and iterate safely. When you're done, you should have a Python script that accepts text input, calls an LLM API securely, and prints the response. The code should be committed, documented, and visible on GitHub. This is your first true AI application built through code. Avoid hard coding API keys, using high temperature everywhere, ignoring API errors, or forgetting to commit changes. These habits cause problems later at scale. Building good discipline now saves significant effort down the line. This lab teaches the most important skill in modern AI development: programmatic access to models. Once you can reliably send input and receive output from an LLM, you can build agents, tools, workflows, and products. Everything else builds on this foundation. Up to this point, you've built the foundations. You understand AI systems. Your environment is set up, and you can talk to models programmatically. Today is where many AI projects either become reliable or quietly fail. Prompt engineering is not about clever wording or tricks. It's about designing a clear contract between your system and the model. When prompts are vague, models guess. When prompts are structured, models behave. Today, we focus on turning prompting from an art into an engineering discipline you can trust. So far, you've made the model respond. Today, you make it respond consistently. That distinction matters. Most frustration with AI comes from prompts that work once and fail the next time. The goal of day 4 is to replace hope with control. You'll learn patterns that make prompts predictable, reusable, and safe enough to use inside real systems. When AI systems fail in production, it's rarely because the model is incapable. More often, it's because the prompt was underspecified. Vague instructions, missing constraints, or unclear outputs give the model too much freedom. Prompt engineering is how you reduce that freedom intentionally. It's the difference between experimentation and engineering. A prompt is not just text. It's an interface between your system and the model. It defines responsibilities, constraints, and expected behavior. If you wouldn't ship vague requirements to a human engineer, you shouldn't ship vague prompts to a model. Treat prompts as specifications, not suggestions. Reliable prompts follow a clear structure. They define the role the model should take, the task it must perform, the context it can rely on, the constraints it must follow, and the format of the output. This structure removes ambiguity. Once you adopt it, prompt behavior becomes far easier to reason about and debug. Separating system instructions from user input is critical. System prompts define behavior and rules. User prompts provide variable content. Mixing these leads to prompt injection risks and unpredictable behavior. Keeping them separate makes your system safer and more stable. Models follow an implicit hierarchy of instructions. System instructions have the highest priority, followed by developer instructions, and finally, user input. If your system rules are weak or unclear, user input can override them. Understanding this hierarchy helps explain why models sometimes appear to ignore you. Never assume the model knows what a good answer looks like. You must define it. Specify the output format, length, tone, and what to do if the model is unsure. Unspecified outputs lead to variability, which is dangerous in production systems. Few-shot prompting means teaching the model through examples rather than explanations. You show it what correct behavior looks like. This reduces ambiguity and often outperforms long instructions. Examples demonstrate patterns the model can follow reliably. Few shot prompting is especially useful for repeatable tasks like classification, extraction, or structured writing. If the task repeats and the format matters, examples are often the most effective form of instruction. They turn abstract rules into concrete behavior. Prompt failures are predictable. Models hallucinate, overconfidently answer, ignore constraints, or make assumptions. These are not mysterious behaviors. They are signals that the prompt failed to set boundaries clearly. Understanding failure modes helps you design prompts defensively. Models hallucinate when they lack information, but are still encouraged to answer. By default, they optimize for completion, not correctness. If you don't explicitly allow uncertainty, the model will guess. Guarding against hallucination starts with allowing the model to say, "I don't know." Guardrails are explicit instructions that prevent bad output. This includes telling the model what to do when unsure, requiring sources, or specifying refusal conditions. Guardrails don't limit usefulness, they increase trust. In production systems, guardrails are essential. A weak prompt like "summarize this document" leaves everything undefined. The model must guess the role, the length, the format, and the purpose. This invites inconsistency. Weak prompts aren't wrong, they're incomplete. A strong prompt defines the role, task, output structure, and constraints clearly. The same task becomes predictable and repeatable. The improvement comes from structure, not fancy wording. This is the core lesson of prompt engineering. In today's lab, you'll take a weak prompt and systematically improve it. You'll identify what's missing, add structure, and convert it into a reusable template. This mirrors real-world work. Prompt engineering is iterative, not theoretical. Before fixing a prompt, diagnose it. Ask what's ambiguous, uncontrolled, or assumed. Most bad prompts fail because the designer skipped this step. You can't engineer reliability without first understanding where uncertainty comes from. Now you add structure. Define the role, clarify the task, add constraints, specify output format, and include guardrails. This step turns a vague request into a specification. Structure always comes before wording refinement. If the task is repeatable, add a few examples. Keep them short and realistic. Examples show the model what success looks like. They reduce the need for long explanations and improve consistency. Finally, turn the prompt into a reusable template. Replace fixed values with placeholders and document how the template should be used. At this point, the prompt becomes a system asset, not a one-off experiment. By the end of day 4, you should have a small library of robust prompts. Each should be structured, reusable, and clearly documented. This library will be reused in future days when you build agents, workflows, and systems. Anyone can write a prompt. Builders design prompts that behave under pressure. From this point forward, your AI systems will depend on the quality of your prompts. Day 4 gives you the control needed to build reliable AI, not just impressive demos. This lab is about changing how you think about prompts. Up to now, you may have been writing prompts the way people give instructions in conversation. That works sometimes, but it doesn't scale, and it doesn't hold up inside real systems. Today, you'll learn to treat prompts as engineered artifacts. You'll take a prompt that works inconsistently, diagnose why it fails, and systematically rebuild it so the model behaves predictably. Then, you'll turn that prompt into a reusable template. This is the skill that separates casual AI use from professional AI development. Today's lab has a simple structure. First, you take a weak prompt and analyze why it fails. Then you redesign it using clear structure and guardrails. Finally, you convert it into a reusable template that can live inside your code base. By the end of this lab, You won't just have a better prompt, you'll have a repeatable process for designing prompts that behave reliably across inputs and use cases. You're building three things today. First, a documented example of a weak prompt. Second, a robust engineered version of that same prompt. Third, a small library of reusable prompt templates. This mirrors real AI work. Teams don't rely on one off prompts. They maintain libraries of prompts that are tested, documented, and reused across systems. Start by choosing a prompt that is genuinely weak. It should be vague, underspecified, and prone to inconsistent results. Do not improve it yet. Capture it exactly as it is. This gives you a clear before and after comparison and helps you see what changes actually matter. Before fixing the prompt, clarify the real task behind it. Ask who the user is, what goal they're trying to achieve, what input the model will receive, and what a successful output looks like. Write this as a single, clear sentence. This sentence becomes the anchor for all design decisions that follow. Now, analyze the weak prompt. Identify what it fails to specify. Is the role unclear? Are constraints missing? Is the output format undefined? Is failure handling absent? List at least three gaps. This diagnosis step is critical. You can't engineer reliability if you don't understand where ambiguity comes from. Next, define the role the model should play. This tells the model how to reason and what to prioritize. Be explicit about responsibilities and priorities, such as accuracy over guessing or clarity over verbosity. A clear role sets behavioral expectations from the start. Now define strict input boundaries. Tell the model exactly what information it may use and what it must ignore. This includes rules like using only the provided input and not following instructions embedded inside that input. These boundaries protect your system from confusion and prompt injection. Next, control the output. Specify the exact format you want, such as bullet points, sections, or structured text. Define length limits and required fields. If you don't specify output clearly, the model will choose its own structure, which leads to variability. Output control is one of the biggest reliability levers you have. Now add guardrails to prevent known failure modes. Tell the model what to do if information is missing, uncertain, unsafe, or out of scope. Guardrails don't reduce usefulness, they increase trust. In real systems, guardrails are what make AI safe enough to deploy. Now add guardrails to prevent known failure modes. Tell the model what to do if information is missing, uncertain, unsafe, or out of scope. Guardrails don't reduce usefulness, they increase trust. In real systems, guardrails are what make AI safe enough to deploy. Before finalizing the prompt, test it deliberately. Try a normal input, a messy or incomplete input, and an adversarial input. Observe how the model behaves. Note where it still fails. Prompt engineering is iterative. Testing is part of the engineering process, not an afterthought. Now finalize the robust prompt. It should include a clear role, a well-defined task, explicit constraints, a controlled output format, and guardrails. Document what changed compared to the weak prompt and why those changes matter. This reflection reinforces good design habits. Next, turn the robust prompt into a reusable template. Replace hard-coded values with placeholders for inputs, tone, or output format. This step transforms a one-off prompt into a system asset. Templates are how prompts scale across projects and teams. Organize your templates into a prompt library. Create a dedicated folder and a single file that contains all templates in a consistent format. Each template should be easy to find, understand, and reuse. Organization matters as much as content. Build a small but useful set of templates across different task types, such as summarization, extraction, classification, rewriting, and planning. The goal is not quantity, it's coverage. Each template should solve a real, recurring problem. For each template, add usage notes. Explain when to use it, when not to use it, and what common failure modes to watch for. Good documentation prevents misuse and makes templates easier to adopt later. This is part of professional prompt engineering. Finally, commit your prompt library to GitHub. Versioning matters. Prompts evolve, and you need to track changes over time. Once committed, your prompt library becomes part of your AI system, not just an experiment. When you're done, you should have a documented weak to robust prompt transformation and a prompt library with reusable templates. This is concrete evidence of prompt engineering skill, not just prompt usage. Anyone can write a prompt that works once. Builders design prompts that behave under pressure. From this point forward, these prompts will power your APIs, agents, and workflows. Reliability starts here. Up to this point, your AI systems have been interacting primarily with humans. They generate text, explanations, summaries, and answers. That's useful, but it's not enough to build real software systems. Today is a turning point. We shift from AI as a conversational tool to AI as a data producing component inside a system. Software cannot interpret responses the way humans do. It needs structure, predictability, and validation. Day 5 is about making AI output safe, reliable, and usable by code. So far, you focused on getting models to respond and behave reliably. Today, you focus on what those responses look like from the perspective of software. The goal of Day 5 is to design AI outputs that machines can consume safely. By the end of today, you'll be producing structured, validated data instead of free-form text. This is a foundational skill for building real AI systems. Humans are good at interpreting messy output. Software is not. Raw text responses change format, vary in wording, and include unexpected commentary. When AI output is consumed by code, even small variations can cause failures. A missing field, extra sentence, or unexpected phrase can break an entire workflow. That's why raw text is fragile in production systems. Raw text breaks down when AI output is passed to another system, stored in a database, or used to make decisions automatically. Any situation where code depends on AI output requires predictability. Without structure, developers end up writing brittle parsing logic or manual cleanup. Both approaches fail at scale. Modern AI systems are rarely the final step. They produce intermediate results that feed into other services, trigger actions, or update records. This means AI must behave like a data producer, not a storyteller. The output needs to be structured, typed, and consistent. That's the mindset shift we make today. Structured output follows explicit rules. It has fixed fields, predictable names, known data types, and clear expectations for what happens when information is missing. Structure allows software to reason about AI output deterministically. It replaces guesswork with contracts. JSON is the default format because it works everywhere. It's language agnostic, easy to parse, and maps directly to objects and data models. When AI outputs JSON, it becomes immediately compatible with APIs, databases, and application logic. JSON is the bridge between AI and software systems. A schema defines the shape of the data. It specifies required fields, optional fields, and expected data types. Schemas reduce ambiguity. They tell both the model and your code exactly what is expected. Without a schema, even JSON can be unreliable. Models do not return structured output by default. You must instruct them clearly. This means explicitly defining the schema, forbidding extra text, and specifying how to handle missing or uncertain values. When prompts are vague, structured output breaks quickly. An unstructured request like summarize and suggest an action leaves everything open to interpretation. A structured version defines exact fields such as summary, severity, and recommended action. The task becomes deterministic. This is what enables automation. Even when asking for JSON, failures are common. Models may add commentary, omit fields, use the wrong data type, or return invalid syntax. You should assume these failures will happen. Robust systems are designed with this assumption in mind. Never trust AI output blindly. Validation is what turns AI from best effort into something safe enough to use. Validation ensures the output parses correctly, contains required fields, and conforms to expectations. Without validation, downstream systems are at risk. Validation typically happens in layers. First, parse the JSON. Next, check required fields. Then, validate types and allowed values. If any step fails, the system should handle it gracefully. Validation is not optional. It is a core part of AI system design. Good AI systems assume failure. They detect invalid output, retry when appropriate, log issues, and fail safely when necessary. Designing for failure is what makes AI usable in production. Ignoring failure modes leads to brittle systems. In today's lab, you'll take a task and force the model to return structured JSON. Then you'll parse that output in Python and validate it before using it. This lab mirrors how AI is integrated into real software systems. Prompting, parsing, validation, and error handling all work together. Before writing the prompt, define the schema. Decide what fields are required, what types they should be, and what values are allowed. Schema-first thinking prevents ambiguity. The model should conform to the schema, not define it. Now, you instruct the model to return valid JSON and nothing else. No explanations, no commentary. You also define how missing or uncertain information should be represented. This clarity dramatically improves reliability. Next, you call the LLM API with your structured prompt. Treat the response as untrusted raw text. At this stage, you are not assuming correctness. You are preparing to verify it. Parsing is the first validation gate. Attempt to parse the response into JSON and handle errors explicitly. If parsing fails, the system should not proceed. This step prevents malformed output from leaking into the rest of your system. Once parsed, validate the data against your schema. Check required fields, data types, and allowed values. Only validated data should be used downstream. This is what protects your application from unpredictable AI behavior. By the end of day 5, you should have a Python function that calls an LLM, returns structured JSON, and validates the output before use. This pattern is production-ready and reusable. It's a core building block for agents, workflows, and automation. Day 5 is the moment AI becomes usable by machines, not just people. From here on, everything you build, agents, tools, workflows, systems, depends on structured, validated AI output. This is what makes AI a reliable component of software systems. Up to now, your AI systems have been producing text that humans can read and interpret. Today, we make a critical shift. We treat AI output as untrusted input to software. That means we must control its structure, validate it, and reject it when it doesn't meet expectations. This lab is about building that discipline. You will force the model to return structured JSON, then parse and validate that output in code. Once you complete this lab, AI stops being a conversational tool and starts behaving like a reliable function inside your system. Today's lab focuses on turning AI output into something software can safely consume. You'll design a strict JSON schema, instruct the model to return only that structure, and then validate the response before using it. This is the pattern that allows AI to integrate into real systems without breaking them. You are building a small but powerful system, a Python script that calls an LLM, forces structured JSON output, parses that output, and validates it before returning data. This pattern is reusable. You will apply it again and again in agents, workflows, and automated systems. Raw AI text is fragile. It changes formatting, includes unexpected commentary, and breaks parsers. Structured data is predictable. It can be validated, stored, and passed between systems safely. This lab teaches you how to make that transition intentionally. Start by choosing a task where structure is clearly needed. Classification, extraction, and structured summaries are ideal. Keep the scope small. Fewer fields and simpler rules make it easier to enforce correctness and see where things break. Before writing any prompt, define the schema. Decide what fields are required, what types they have, and what values are allowed. Schema first thinking reduces ambiguity. The model's job is to conform to the schema, not invent it. Now decide what should happen when the model is uncertain or information is missing. Should it return a special value like unknown? Should confidence be lowered? These rules must be explicit. If you don't define failure behavior, the model will guess. Your system prompt must be strict. Require valid JSON only. Forbid explanations, markdown, or extra text. Include the schema directly in the prompt. This is where most reliability gains come from. Precision here saves debugging time later. Always separate system rules from user input. System messages define constraints and schema. User messages provide raw content. This separation protects your prompt from injection and keeps behavior consistent across inputs. Now, call the LLM API using your structured prompt. Capture the response as raw text. At this stage, assume nothing. Treat the output as untrusted until it passes validation. Before parsing, inspect the raw output. Look for extra text, formatting issues, or missing fields. Seeing the raw output helps you debug prompt issues quickly and understand how the model behaves under constraints. Parsing is your first validation gate. Attempt to parse the output using a JSON parser. If parsing fails, stop immediately. Do not try to repair malformed JSON silently. Failing fast is safer than guessing. Once parsed, verify that all required fields are present and non-empty. Missing fields mean the output does not meet the contract. Reject it cleanly and explicitly. Next, validate data types and allowed values. Strings should be strings. Numbers should fall within expected ranges. Categories should match predefined lists. This protects downstream systems from subtle errors. Optionally, normalize the data. Convert numeric values to consistent types. Standardize casing and remove unexpected fields. Normalization simplifies downstream logic and reduces edge cases. Once the data passes all checks, return it from your function or pass it to the next step in your system. At this point, AI behaves like a function. Input goes in, validated data comes out. Designed for failure. When validation fails, log the error, reject the output, and optionally retry with stricter prompts. Never silently accept invalid AI output. Failure handling is part of system design. When you're done, you should have a Python function that calls an LLM, forces structured JSON output, parses it, validates it, and returns safe data. This is a production-ready pattern you will reuse often. Structured, validated AI output is the foundation for agents, tools, workflows, and automation. This lab marks the point where AI becomes a reliable system component instead of a conversational interface. Everything that follows builds on this. Up to now, your AI systems have been operating without memory or private knowledge. They respond based on prompts, structure, and APIs. but they don't actually know anything about your documents, policies, or internal data. Day 6 introduces the most important pattern for real world AI: retrieval augmented generation, or RAG. Instead of trying to make models remember, we retrieve relevant information at query time and ground the model's response in that data. This is how modern AI systems answer questions over documents reliably, without retraining models or exceeding token limits. So far, your AI systems have been general purpose. They know language, but they don't know your data. Today, you change that. You will build a system where AI answers questions using your documents as a source of truth. The goal is not memory, it's controlled access to knowledge through retrieval. Language models do not retain memory across requests. Each API call is stateless unless you explicitly provide context. They also do not have access to your private documents by default. If the information isn't in the prompt, the model doesn't know it exists. Understanding this constraint is key to designing correct systems. A common mistake is trying to paste documents directly into prompts. This quickly runs into problems: token limits, high cost, slow responses, and loss of important context. Prompting alone does not scale for knowledge-heavy tasks. You need a system that selectively provides only the most relevant information. Retrieval augmented generation solves this by splitting the problem in 2 steps. First, retrieve relevant information. Second, generate an answer grounded in that information. The model is not remembering anything. It is reasoning over retrieved context provided at the time of the question. A RAG system has several components: documents, embeddings, a vector store, a retriever, and an LLM. Each part has a clear role. Documents hold knowledge. Embeddings capture meaning. The retriever finds relevant chunks. The model generates answers using retrieved context. RAG is a system, not a single feature. Embeddings convert text into numeric vectors that represent meaning. Similar meanings result in vectors that are close together. This allows us to compare questions and document chunks mathematically, rather than relying on exact keyword matches. Semantic search finds content based on meaning, not exact words. A question can retrieve relevant passages even if the wording is different. This is why embeddings are effective for document Q&A. They capture intent, not just text overlap. A vector database stores embeddings and supports similarity search. Given a query vector, it returns the most similar document vectors. The implementation can vary, but the idea stays the same. Store meaning, retrieve by similarity. Documents must be split into chunks before embedding. Chunk size is a design decision. Chunks that are too large include irrelevant context. Chunks that are too small lose meaning. Good chunking balances precision and context. When a user asks a question, the system embeds the question, retrieves the most relevant chunks, injects them into the prompt, and then asks the model to answer. The model's answer is grounded in retrieved data, not memory. This is the core RAG loop. RAG and fine-tuning solve different problems. RAG is ideal for dynamic, private, or frequently changing knowledge. Fine-tuning changes model behavior, not knowledge. For most document-based use cases, RAG is the correct choice. RAG systems can fail if chunking is poor, retrieval is weak, or irrelevant context is injected. Hallucinations can still happen if the model is not instructed to rely strictly on retrieved content. System design matters as much as the model. RAG improves trust because answers are grounded in source material. You can inspect retrieved chunks and trace why an answer was produced. This makes AI output more explainable and defensible, especially in enterprise settings. In today's lab, you will build a basic RAG pipeline. You'll load documents, chunk them, embed them, retrieve relevant chunks, and generate answers over your own data. This mirrors how real-world knowledge assistants are built. The first step is loading documents into your system. This can include text files or PDFs. Clean the content and remove noise. Retrieval quality depends on input quality. Garbage in still leads to garbage out. Next, split documents into chunks. Choose a chunk size that preserves meaning without including too much unrelated text. Chunking strategy has a major impact on retrieval accuracy. Treat it as a design decision, not a default. Now generate embeddings for each chunk and store them with metadata. This step creates your searchable knowledge index. Once embeddings are stored, retrieval becomes fast and scalable. When a question arrives, embed the query and perform a similarity search against stored embeddings. Select the top relevant chunks. Retrieval quality directly determines answer quality. Inject retrieved chunks into the prompt and instruct the model to answer using only that context. This is retrieval augmented generation in action. The model reasons over provided knowledge, not assumptions. By the end of day 6, you should have an AI assistant that answers questions over your documents using retrieval. The assistant does not remember. It retrieves and reasons. That distinction is critical. Day 6 unlocks real-world AI use cases. Internal knowledge bases, document Q&A, policy assistance, and research tools. This is where AI becomes genuinely useful in professional environments. Everything that follows builds on this pattern. In this lab, you're going to give your AI system access to knowledge without pretending the model has memory. That distinction matters. Models don't remember documents. Systems retrieve them. What you're building today is a retrieval pipeline. Documents go in, embeddings are created, relevant context is retrieved, and only then does the model generate an answer. This is the most widely used pattern for building knowledge-aware AI systems in the real world. Focus on understanding the flow, not just making it work once. Today's lab is about turning static files into usable knowledge. You'll start with documents on disk, convert them into embeddings, and then ask questions that are answered using those documents. By the end of this lab, your AI assistant will not guess or hallucinate. It will retrieve relevant context and reason over it. You're building a complete end-to-end pipeline, not just a prompt. This includes document ingestion, chunking, embedding, retrieval, and answer generation. Each part plays a specific role, and weaknesses in any step affect the final answer. Think of this as building infrastructure, not a demo. Before starting, make sure your environment is stable. Your Python environment should be active, your API key should be loaded from .env, and your repository should run cleanly. Most RAG issues are not model issues, they're setup issues. Fix those first. Start by adding documents to your system. Use clean, readable text files to begin with. Avoid dumping raw or noisy data. The system can only retrieve what you give it, and poor input quality leads to poor retrieval. Next, load those documents into your code. At this stage, no AI is involved. Your goal is to reliably read files, assign document identifiers, and get raw text into memory. If this step is fragile, everything downstream will be too. Before chunking or embedding, clean the text. Normalize whitespace and remove obvious noise. Embeddings capture meaning, but they're still sensitive to garbage input. Clean text improves both retrieval accuracy and efficiency. Documents must be split into chunks. This is a design decision, not a mechanical step. Chunks that are too large include irrelevant information. Chunks that are too small lose context. Use overlap to preserve continuity between chunks. Now you convert chunks into embeddings. This step transforms text into numeric vectors that represent meaning. Each chunk becomes searchable by semantic similarity. This is what allows your system to retrieve relevant information later. Once embeddings are created, store them along with chunk text and metadata. This index is your knowledge base. It should be easy to rebuild, inspect, and version. Treat it as derived data, not a permanent artifact. Now the user enters the system. Accept the question as raw input. Just like documents, questions are untrusted input. They must go through the same embedding process before retrieval can happen. Embed the user's question using the same embedding model you used for documents. This ensures the query vector lives in the same semantic space as your document vectors. Consistency here is critical. Perform similarity search between the question embedding and stored document embeddings. Select the top K most relevant chunks. Retrieval quality is the single biggest factor in RAG performance. Before generating an answer, inspect what was retrieved. If the retrieved chunks are irrelevant, the model will fail no matter how good the prompt is. Debug retrieval before touching the generation step. Now, build a grounded prompt. Inject retrieved chunks into the prompt and instruct the model to use only this context. Explicitly tell the model what to do if the answer is not found in the context. This prevents hallucinations. Call the LLM with the grounded prompt. At this point, the model is not answering from memory. It is reasoning over retrieved knowledge. This is retrieval augmented generation. If the retrieved context does not contain the answer, the system should say so clearly. A correct "I don't know" is more valuable than a confident hallucination. This is how trust is built. By the end of this lab, you should have a document-aware AI assistant. It loads documents, retrieves relevant context, and answers questions grounded in that data. No memory, no guessing, just retrieval and reasoning. This pattern is the foundation for most enterprise AI systems: internal search, policy assistance, research tools, and compliance systems. Once you understand this flow, you can scale it, optimize it, and adapt it to more complex use cases. Up to this point, everything you've built has lived in scripts, terminals, and code files. That's normal for developers, but it's not how most people experience software. Today is about crossing that boundary. Day 7 is where your AI stops being a developer-only tool and starts behaving like a product. You're not learning full-stack engineering. You're learning how to wrap AI logic behind a simple interface so users can interact with it safely and intuitively. This is a critical step in turning AI experiments into usable systems. So far, your AI systems have required a terminal and technical knowledge to use. Today, you change that. The goal of Day 7 is to connect your existing AI logic to a simple web interface. By the end of the day, your AI will respond to user input through a browser, not a command line. That shift is what turns code into a product. Scripts are powerful, but they're not accessible. They assume the user understands how to run code, pass arguments, and read logs. Products, on the other hand, are designed for interaction. They guide users, handle mistakes, and present output clearly. Adding a UI doesn't change your AI logic, but it completely changes who can use it. A simple AI web app has 3 main parts: a front end, a back end, and an API that connects them. The front end collects user input and displays results. The back end runs your AI logic. The API is the contract between the two. Keeping these responsibilities separate makes systems easier to reason about and extend. The back end is responsible for everything sensitive and complex. This includes API keys, AI calls, validation, and error handling. The front end is responsible for interaction. It gathers input and shows output. Mixing these responsibilities leads to security and maintenance problems, so separation matters even in small apps. The front end never talks directly to the AI. It talks to an API endpoint exposed by the back end. This gives you control. You can validate input, enforce limits, and change AI logic without touching the UI. APIs are what allows systems to evolve safely. For this lab, simplicity is the goal. You don't need a heavy framework or complex tooling. A lightweight Python backend and a basic HTML interface are enough to demonstrate the full flow. The focus is understanding how the pieces connect, not mastering web development. Every interaction follows the same loop. The user enters input. The front end sends it to the back end. The back end calls the AI. The result is returned and displayed. If you understand this loop, you understand the core of most AI-powered products. Each API endpoint should do one thing well. It should accept structured input, call the AI logic, and return structured output. Think of your AI as a function. The endpoint is the wrapper that makes it usable over the web. Never expose secrets in the front end. API keys, prompts, and internal logic belong on the back end. Assume user input is untrusted. The back end exists to protect both your AI system and the services it depends on. In today's lab, you'll build a minimal but complete AI web app. You'll create a backend server, expose an AI endpoint, build a simple UI, and connect the two. Everything runs locally, but the architecture mirrors real production systems. The first step is wrapping your existing AI logic in a web server. You're not rewriting AI code, you're exposing it through an endpoint that can be called by the front end. This is where your AI becomes a service. Before building the UI, define what the API expects and what it returns. Clear input and output contracts prevent confusion and bugs. This also makes it easier to test the backend independently of the front end. Now build a minimal interface. An input box, a button, and an output area are enough. The goal is usability, not design. If a user can enter text and see a response, the UI has done its job. This is the key moment. The front end sends a request to the backend API and receives a response. Once this works, you've completed the full loop, user to AI and back again. Everything else is iteration. Users will submit empty input, unexpected text, or repeat requests. Your app should handle these cases gracefully. Clear error messages and safe fallbacks improve trust and usability. Test your app like a user would. Refresh the page. Submit multiple inputs. Try edge cases. If the app works reliably on your machine, it meets the goal of this lab. By the end of day 7, you should have a working AI web app running locally. It should have a backend API, a simple UI, and a clear flow from input to AI output. This is your first complete AI product. This day marks a shift in mindset. You're no longer just building AI logic. You're building experiences. Once AI has a UI, it becomes accessible, testable, and iteratable. This is how AI systems move from experiments to real-world use. In this lab, you're going to take AI logic you've already built and make it usable through a browser. This is a subtle but important shift. You're not changing what the AI does. You're changing how people interact with it. The goal today is not to become a front-end or back-end expert. The goal is to understand the flow. User input goes to an API, the API calls AI logic, and the result comes back to the user. Once you understand that loop, you can build real AI products. Today's lab is about connection. You already have AI logic that works in a script. Now you'll build a simple web interface and connect it to that logic. By the end of this lab, your AI will respond to input from a browser. That change alone dramatically increases who can use your system. You're building a minimal but complete AI product. It has a backend that runs AI logic and a front end that users interact with. This is not a demo. It's the smallest possible version of a real system. Input, processing, and output. all connected. At a high level, your app has three parts. The front end collects input. The back end processes requests and calls AI. The API connects the two. Each part has a single responsibility. Keeping these responsibilities separate is what makes systems understandable and maintainable. The first step is wrapping your existing AI logic in a server. This server will expose your AI as a service. All sensitive information, including API keys and prompts, stays on the back end. The front end never talks directly to the AI. Next, you define an API endpoint. This endpoint accepts user input and returns AI output. Think of this endpoint as a function over the network. Clear inputs and outputs make everything else simpler. Before building the UI, define what the API expects and what it returns. Decide what fields are required, what the response looks like, and how errors are represented. This contract prevents confusion later. Now, start the backend server locally. Confirm that it runs without errors and responds to requests. Do not move on until this works. A stable backend is the foundation for the UI. Now build a minimal web interface. You only need a text input, a submit button, and an output area. Ignore styling. Focus on functionality. If a user can enter text and see a response, the UI is doing its job. Next, capture user input from the UI. Validate it before sending it to the backend. User input is always untrusted. Even simple checks, like preventing empty input, improve reliability. This is the key step. The front end sends a request to the backend API with the user's input. Once this works, you've connected the UI to your AI system. Everything else is refinement. The backend returns a response, usually as JSON. The front end must parse this response and check whether the request succeeded. Never assume success. Always handle error cases explicitly. Now display the AI output in the UI. Preserve formatting and update the output area cleanly. This is what users actually experience. Clear output matters more than fancy design. Users will submit bad input. Networks will fail. APIs will sometimes error. Your app should handle these situations gracefully. Clear error messages build trust and reduce frustration. Test the entire system end to end. Try different inputs. Reload the page. Submit edge cases. If the app behaves consistently, you've built a real product, not just a prototype. By the end of this lab, you should have a working AI web app running locally. It should include a backend API, a simple browser UI, and a complete flow from user input to AI output. This lab changes how you think about AI. You're no longer just writing code that works. You're building systems people can use. Once AI has a user interface, it becomes testable, accessible, and improvable. This is the foundation for everything that comes next. Up to now, every AI interaction you've built has effectively started from zero. The model responds, but it doesn't remember what happened before. That's fine for demos, but it breaks down quickly in real applications. Day 8 is about adding memory and managing state. You'll learn how to persist context across turns, how to decide what should be remembered, and how to design systems that feel coherent over time. This is not about clever prompting, it's about architecture. So far, your AI systems have been stateless. Each request is isolated. Today, you introduce memory. That means conversations persist across turns, and users don't have to repeat themselves. This is the step that turns interactions into conversations. AI feels forgetful because most systems reset on every request. The model does not retain information unless you explicitly provide it again. Without stored context, conversations lose continuity and feel unnatural. Stateless AI treats every request as new. Any context must be resent every time. Stateful AI simulates memory by storing and replaying context. The model itself remains stateless. The system around it provides continuity. State is just data. It includes conversation history, session metadata, and user specific context. Nothing magical is happening inside the model. State lives in your application and is injected into prompts as needed. Memory can be short term or long term. Short term memory helps maintain conversational flow. Long term memory persists across sessions and captures durable information about the user. They serve different purposes and must be handled differently. Short term memory tracks the current conversation. It's limited in size and often managed as a sliding window or summarized context. It answers the question, what are we talking about right now? Long term memory stores durable facts, preferences, or summaries. It survives session restarts and is explicitly retrieved. Long-term memory should be written carefully and sparingly. Appending every message to the prompt leads to token bloat, higher costs, and slower responses. More context does not always mean better answers. Memory must be curated, not accumulated. Common strategies include keeping a sliding window of recent turns, summarizing older context, or storing key facts separately. The right strategy depends on the application. Memory design is a system decision, not a model feature. Memory only makes sense if you know who the conversation belongs to. Session IDs or user IDs allow you to associate stored context with the correct conversation. Without identity, memory is meaningless. Memory lives outside the model. It can be stored in memory, files, or databases. The model never stores state. It consumes whatever context you provide. Reading memory and writing memory are separate decisions. Before responding, you decide what memory to load. After responding, you decide what to save. Not every interaction deserves to be remembered. Storing incorrect or temporary information can harm future interactions. Memory should be validated and occasionally corrected or deleted. Bad memory is worse than no memory. RAG retrieves factual knowledge from documents. Memory maintains conversational context. They complement each other. RAG answers what is true. Memory answers what is relevant right now. In today's lab, you'll add memory to your AI app. You'll track sessions, store conversation turns, and replay context into prompts. This transforms your app into a multi-turn conversational system. The first step is identifying the conversation. You'll generate a session ID and attach it to each request. This allows you to retrieve the correct memory for each user. Next, you store each user input and assistant response. Keep the structure consistent and avoid storing unnecessary data. Memory should be usable and inspectable. Before calling the model, load recent conversation turns and inject them into the prompt. Limit how much you include. Only context that improves the response should be replayed. Persist session data so memory survives restarts. Store sessions to disk or a database and clean up old sessions. Persistence makes memory real. By the end of day 8, you should have a multi-turn conversational AI app. It remembers context across turns, uses session-based memory, and persists state reliably. This is the point where AI apps start to feel coherent. Memory turns isolated responses into conversations. It's the difference between a demo and a usable product. In this lab, you're going to move from single-turn interactions to real conversations. That doesn't happen by changing prompts. It happens by designing state. You'll add session identity, store conversation turns, replay relevant context, and persist everything so it survives restarts. The model itself remains stateless. Your application is what creates continuity. Focus on understanding the flow of data and decisions around what to store, what to replay, and what to forget. Today's lab is about adding memory to your AI app. You will track conversations across turns and persist them so users don't have to start over. By the end, your app will behave like a real chat system, coherent, continuous, and session aware. You're building session based conversation memory. Each user gets a session, each session has a message history, and that history is used to inform future responses. This is not a feature of the model, it's an architectural layer you control. You're starting with a working AI web app from day 7. It already accepts input and returns responses. Today, you're extending it. You're not rewriting the app. You're adding state on top of the system that already works. The first step is identifying which conversation a request belongs to. You do this by introducing a session ID. Every request must include this ID. Without it, the backend cannot associate messages with the correct conversation. The browser is responsible for remembering who the user is. You generate a session ID once and store it locally. This ensures that page refreshes don't reset the conversation. The browser remembers the session, and the backend uses it to load memory. Next, you create a session store on the backend. This is where conversation memory lives. The session store maps session IDs to structured message histories. This data must be easy to inspect, update, and persist. Each message in memory should have a consistent structure. At minimum, store the role, the content, and a timestamp. Structured memory is manageable memory. Inconsistent structures lead to bugs and confusion later. Every time a user sends a message, you append it to the session's history. Every time the assistant responds, you store that response too. You are deliberately writing memory. Not everything needs to be remembered, but what you do store should be intentional. Before generating a response, you load recent messages for the session. This is your short-term conversational memory. Limit how much you load. More context is not always better. Only include what helps the model stay coherent. Now, you replay the selected memory into the prompt. Keep system instructions separate from conversation history. This step simulates memory for the model. The model reasons over what you provide, nothing more. You now call the model with a message list that includes system instructions, replayed history, and the new user input. This is where multi-turn behavior emerges. The model can reference earlier turns because you provided them. In-memory memory disappears when the server restarts. To make memory real, you persist sessions to disk or a database. On startup, load persisted sessions back into memory. Persistence is what makes conversations durable. Memory cannot grow forever. You must clean up old or inactive sessions, set expiration rules, and remove stale data. Memory management is part of system health. Your API now requires a session ID. Make that explicit in the request schema. Validate it on every request and return clear errors when it's missing. State should never be implicit. Test whether the system remembers. Ask follow-up questions. Refer to earlier messages. Ask for a summary of the conversation. If the AI stays coherent, your memory system is working. Restart the backend server and refresh the browser. Continue the conversation. If the AI still remembers, persistence is working. This is a critical validation step. By the end of this lab, you should have a multi-turn conversational AI app. It uses session-based memory, persists conversations, and behaves coherently across turns and restarts. This lab is the difference between a demo and an application. Memory enables continuity, trust, and usability. Once you understand how to design and manage state, you can build real conversational products. Up to this point, you've built systems that respond intelligently, They understand input, maintain memory, and generate coherent answers. But they still depend on a human to take action. Day 9 changes that. Today, you move from conversational AI to action taking systems. You will learn what actually makes something an agent, how tools extend model capabilities, and how to build a controlled execution loop. This is where AI stops being reactive and starts being operational. Until now, your systems have been conversational. They respond when prompted. Today, you introduce agency. An agent is built to complete a goal, not just generate a reply. The objective is to design a system that can reason, select tools, execute actions, and iterate toward completion. Chatbots are constrained to text generation. They can explain, summarize, and reason, but they cannot directly modify the world around them. If you want your system to search the web, manipulate files, call APIs, or perform calculations, you need more than generation. You need tools. An AI agent is a goal-driven system. It receives an objective, determines what steps are required, selects appropriate tools, executes them, evaluates results, and continues until the task is complete. The defining feature is iterative execution. Every agent consists of 4 components: a reasoning engine, a tool set, a control loop, and memory or state. The model performs reasoning. Tools perform actions. The loop coordinates everything. Memory provides continuity across steps. Language models are powerful predictors of text, but they do not inherently have access to external systems. Tools allow the model to interact with code, APIs, files, or databases. Tools are structured interfaces that extend the model's capabilities beyond language. Before acting, an agent often plans. It decomposes a goal into smaller steps and determines which tools are required. Planning reduces ambiguity and prevents chaotic execution. It allows structured progress toward a defined objective. The core of an agent is the execution loop. Think, act, observe, repeat. The model reasons about the goal, selects an action, executes it, observes the result, and decides whether to continue or stop. This cycle defines agent behavior. A chatbot produces responses. An agent produces outcomes. Chatbots operate in single steps. Agents operate across multiple steps and use tools to influence their environment. That distinction is foundational. You do not need a complex framework to build an agent. Start with one goal, a small set of tools, and a controlled loop. Simplicity makes the system understandable and debuggable. Agents must operate within constraints. You should define iteration limits, tool restrictions, and stopping conditions. Autonomy without boundaries leads to instability. Control is part of responsible design. In this lab, you will define tools, register them with the model, allow the model to call them, and implement an execution loop. By the end, your system will complete real tasks autonomously. Tools are just structured functions. Each tool has a name, parameters, and a defined output. Examples include search functions, file readers, or calculation utilities. Keep tools simple and deterministic. The model must understand how to call tools. You expose structured schemas that describe each tool's parameters and purpose. Clear schemas allow the model to generate structured tool calls correctly. With tool schemas available, the model can decide when to call a function instead of generating plain text. This is controlled autonomy. The model chooses actions, but only from the tools you provide. When the model requests a tool call, your backend executes the corresponding function. You capture the result and feed it back into the conversation so the model can continue reasoning. The agent loop repeats until the task is complete. Each iteration includes reasoning, action, and observation. You must define when the loop stops. Completion criteria are critical. Add limits to prevent infinite loops. Validate tool inputs. Log each action for debugging. These guardrails make the system predictable and safe. Your agent might research a topic, summarize findings, save outputs to a file, or process structured data. The key is that the agent performs measurable actions that move toward a goal. By the end of day 9, you should have a goal-driven AI agent capable of selecting and executing tools in a loop. This is no longer a chat system. It is an action-taking system. This is a foundational shift. You are now designing systems that can automate workflows and interact with external environments. Agents form the backbone of modern automation systems. Understanding this architecture prepares you for orchestration, multi-agent systems, and enterprise-scale AI. In this lab, you are moving from conversational AI to operational AI. Up to this point, your systems have generated intelligent responses. Now you will build a system that can take action. The goal today is not to create an autonomous superagent. It is to understand the minimal architecture required for action: tools, a reasoning loop, and bounded execution. If you understand this pattern clearly, you can scale it later. We are building the foundation. Today, you will build an agent that completes tasks rather than just responding to prompts. The system will receive a goal, decide what tools to use, execute them, and iterate until the task is complete. This introduces structured autonomy into your architecture. You are building a CLI-based AI agent with a defined tool registry and execution loop. The deliverable is not just code. It is a system that can create files, search documents, calculate values, and produce real outputs inside a controlled environment. Before writing code, understand the architecture. You have a goal input, a reasoning engine powered by the model, a set of tools, and an execution loop. The loop coordinates reasoning and action until completion. Understanding this structure prevents confusion during implementation. Let's look into tool design. The agent can only act through tools you explicitly define. Start with a small, controlled set. Search local documents, read files, write files, and perform calculations. These tools define the boundaries of your agent's capabilities. Each tool is a deterministic Python function. It accepts structured parameters and returns structured JSON. Tools should be predictable and handle errors gracefully. Avoid side effects beyond what is necessary. File operations are powerful and risky. You must restrict file access to a specific workspace directory and prevent path traversal. This ensures your agent cannot accidentally modify unintended parts of the system. Let's look into exposing tools to the model. The model must know how to call tools correctly. For each tool, define its name, description, parameters, and required fields. Clear schemas reduce ambiguity and improve structured tool calls. Create a mapping from tool names to Python functions. This registry is what allows your agent to translate a model's tool call into an actual code execution. It is the bridge between reasoning and action. When calling the model, include the tool schemas and allow the model to choose tools automatically. This is where conversational AI becomes agentic AI. The model now decides when to act instead of only generating text. Let's look at execution loop. The loop begins with the system instructions and the user's goal. The model analyzes the goal and determines the next action. That action might be a tool call or a final answer. After each model call, inspect the response. If the model produces tool calls, you execute them. If it produces only text without tool calls, you treat it as the final result. This conditional logic defines your agent's control flow. When a tool call is detected, parse the arguments and call the corresponding Python function. Capture the result in structured form. Tool execution must be deterministic and reliable. After executing a tool, append its output back into the message history. Then call the model again. The model observes the result and decides the next action. This completes one cycle of the think, act, observe loop. Agents must not run indefinitely. Define a maximum number of iterations. If the loop exceeds that number, terminate gracefully. This prevents runaway execution and enforces discipline. Let's look at testing and validation. Test tasks that require the search tool. Ensure the agent calls the search function and incorporates retrieved information into the final output. Verify that tool usage is visible and traceable. Test tasks that require writing to the workspace. Confirm that files are created correctly and contain expected content. This verifies that the agent can perform real external actions. Now, test compound tasks that require multiple tools. For example, search documents and then write a summary file. Confirm that the agent chains actions logically and stops when complete. By the end of this lab, you should have a functioning CLI agent, a registered toolset, a bounded execution loop, and real outputs in the workspace. This is a working agent, not a conversational assistant. This lab represents a structural shift in your AI development path. You are no longer building systems that only generate answers. You are building systems that produce outcomes. This pattern underlies automation, enterprise workflows, and advanced AI systems. Understanding this loop is foundational for everything that follows. Up to this point, you've built intelligent systems that respond, remember, and act. But they still depend on you to initiate execution. Real automation begins when AI runs because something happened, not because someone typed a prompt. Day 10 is about designing workflows, structured, repeatable pipelines triggered by events. You'll learn how to chain AI steps, design triggers, manage outputs, and insert human review where needed. This is how AI becomes operational infrastructure rather than an interactive tool. Yesterday, you built an agent capable of completing tasks. Today, you go one level higher. Instead of completing one goal at a time, you'll design repeatable workflows that trigger automatically and execute multiple steps in sequence. This shifts your thinking from single execution loops to orchestrated pipelines. Automation removes the need for manual prompting. Instead of a human initiating a request, a system reacts to an event. A trigger occurs, the workflow runs, and outputs are generated without intervention. This is the foundation of scalable AI systems. Every workflow begins with a trigger. Triggers can be time-based, file-based, API-based, or user-generated. The important principle is determinism. When a defined event happens, the workflow starts. This makes behavior predictable and testable. An agent solves one goal interactively. A workflow orchestrates multiple actions across steps. Workflows move data through structured stages and often involve multiple AI calls. The focus shifts from reasoning loops to controlled sequencing. Every workflow has 5 parts: a trigger, processing steps, decision logic, outputs, and optional human oversight. Defining these clearly before coding reduces ambiguity and makes the system easier to maintain. In workflows, outputs from one step become inputs for the next. For example, extract content, analyze it, summarize findings, save the result, and notify stakeholders. This chaining creates deterministic pipelines instead of isolated AI calls. Sequential steps depend on each other. Parallel steps can run independently. Understanding dependencies allows you to design efficient workflows. Many real systems combine both patterns. Not all automation should be fully autonomous. Human checkpoints can validate outputs, approve sensitive actions, or intervene when confidence is low. Good workflow design balances autonomy and oversight. Insert review when risk increases. Financial decisions, legal communication, and irreversible actions should not execute blindly. Human in the loop design is not weakness, it is responsible architecture. Most workflows follow common patterns: extract, transform, save, classify, route, notify, monitor, trigger, act. Recognizing patterns allows you to design systems faster and with fewer mistakes. Workflows can be implemented using simple Python scripts, schedulers, webhooks, or automation platforms. The tooling matters less than the architecture. Clear triggers, structured steps, and controlled outputs are what make automation reliable. In today's lab, you will build a complete workflow. You will define a trigger, implement multiple AI steps, chain outputs between them, and produce a final artifact. The system should run deterministically and repeatably. Choose a meaningful use case. Automation should solve a real recurring task, such as processing reports or summarizing support tickets. Starting with a real problem makes design decisions clearer. Define what starts the workflow. It might be a file appearing in a directory, a scheduled execution, or an API call. The trigger should be simple and clearly defined. Before coding, map the steps. Write down the order of operations. Define inputs and outputs for each stage. This planning prevents confusion during implementation. Each workflow stage should be implemented as a separate function. Functions should accept structured input and return structured output. Modular design makes debugging and scaling easier. Now connect the functions. Pass outputs from one function into the next. Ensure data transformations are clear and deterministic. This chaining is what creates the pipeline. Automation must be observable. Log when triggers fire, when steps execute, and when outputs are produced. Logging allows you to trace behavior and diagnose failures. If your workflow produces drafts or sensitive outputs, insert a review checkpoint. This might involve writing a draft file for approval or flagging uncertain results. Human oversight increases reliability. By the end of this lab, you should have a repeatable, trigger-based workflow. It should process input, execute multiple AI steps, produce structured output, and log execution. The system should run consistently without manual prompting. This day represents a structural evolution in your AI development journey. You've moved from interactive systems to automated pipelines. This is the foundation of AI operations, business automation, and production AI systems. Understanding workflows prepares you for deployment, scaling, and orchestration in real environments. In this lab, you are moving from task-level automation to system-level automation. The difference is subtle but critical. An agent completes a goal when asked. A workflow executes automatically because an event occurred. Today, you will design and implement a real end-to-end automation pipeline. You will define a trigger, chain multiple AI steps, apply deterministic business logic, generate structured outputs, and log the results. By the end, you will have a repeatable system that processes inputs without manual prompting. This is how AI transitions from interactive tools to operational infrastructure. In this lab, your objective is to build a complete multi-step AI workflow. Instead of a single reasoning loop, you will construct a pipeline composed of discrete stages. Each stage performs a specific responsibility, and the system executes from start to finish without manual intervention. The emphasis today is not creativity, but structure. Automation requires predictability. By the end of this lab, you should have a system that reacts to a trigger, processes input through multiple AI-powered steps, produces structured outputs, and logs its execution. This is how AI begins functioning as back-end infrastructure rather than as an interactive assistant. We are implementing a realistic automation scenario. A text file appears in an input directory. That file contains unstructured content, perhaps a support request report, or message. Your workflow will extract structured data from that file, classify it, generate a response draft, and save the outputs automatically. The purpose of choosing a file based trigger is simplicity and determinism. It allows you to focus on workflow structure without the complexity of external integrations. This use case mirrors many real world systems where new data enters a pipeline and must be processed consistently. Automation begins with a trigger. In this lab, the trigger is the presence of a new text file inside the inbox directory. When a file appears, the system detects it and initiates processing. The important principle is determinism. The workflow should always start under clearly defined conditions. There is no manual prompt. There is no ambiguity. Triggers can be time-based, event-based, or API-based. Here, we are using a folder watcher to simulate an event-driven architecture. The trigger defines when your system activates. Before writing code, map the workflow stages clearly. We divide the pipeline into 6 stages: load input, extract structured JSON, classify and route, generate draft response, save outputs, and log execution. Each stage has one responsibility. That separation is critical. Mixing responsibilities leads to fragile systems. By defining steps in advance, you reduce cognitive load during implementation and ensure that data flows logically from one stage to the next. Each workflow stage should be implemented as a separate function. A function accepts defined input and returns structured output, nothing more. Modularity enables easier testing, debugging, and scaling. If extraction fails, you know exactly where to inspect. If classification rules change, you update a single function. Workflows should resemble assembly lines, where each component performs one precise operation before handing off to the next. This is the first AI-powered step. You transform raw text into structured JSON. The goal is to convert unstructured content into predictable fields such as topic, requester, urgency, summary, and action items. The model must return valid JSON and nothing else. Determinism is critical here because downstream steps depend on this structure. If extraction fails, the workflow should halt safely. Structured outputs create stability across the pipeline. Not every step requires AI. Once structured data is extracted, you apply rule-based logic. For example, urgency determines routing and service level agreement. High urgency may trigger a priority workflow, while low urgency may route to a delayed queue. Separating AI reasoning from deterministic rules improves reliability and reduces cost. AI interprets. Rules enforce policy. Now that you have structured data and routing logic, you use AI again to generate a draft response. This step is creative but controlled. The model is grounded in structured inputs and does not invent context. It produces a professional response draft aligned with extracted fields. AI is used where language generation is needed, but it operates within strict boundaries defined earlier in the workflow. The orchestrator connects all steps. It calls each function in order and passes outputs forward. This component ensures the workflow behaves predictably. It should also stop execution immediately if a step fails. The orchestrator is the backbone of automation. It ensures that no stage is skipped and that data flows cleanly through the pipeline. Workflows must fail safely. If extraction fails or structured validation fails, the pipeline should stop and log the issue. Partial outputs create confusion and risk. A clean failure with clear logging is better than incomplete automation. Design your workflow so that each step checks for success before proceeding. At the end of the workflow, save artifacts. These might include structured JSON results and a draft text file. Outputs must be inspectable and versionable. This ensures traceability and accountability. Saving structured outputs transforms your AI pipeline into something operational and auditable. Automation without logging is dangerous. Log when triggers fire, when steps complete, and whether errors occur. Logs allow you to diagnose issues and validate system behavior. Observability is essential for production workflows. The folder watcher simulates event-driven automation. It continuously monitors the inbox directory and triggers the workflow when a new file appears. After processing, the file is moved to a processed folder. This prevents duplicate runs and maintains system cleanliness. This simple polling mechanism models how real event-driven systems operate. Testing validates the architecture. Drop a test file into the inbox and observe the system behavior. Confirm that structured outputs are generated, draft files are created, logs are updated, and the original file is moved. Repeat with multiple files to ensure repeatability. Automation does not mean eliminating humans. Insert review checkpoints where risk is high. For example, save draft responses for approval before sending externally. High urgency items may require human validation. Human in the loop design balances efficiency with safety. By the end of this lab, you should have a fully operational AI workflow that runs automatically. It should detect new input, process multiple AI steps, produce structured outputs, log execution, and repeat consistently. This is not an AI demo, it is a working automation pipeline. This lab transitions you from interactive AI development to operational AI engineering. You have now built systems that respond, remember, act, and automate. This is the foundation for production AI infrastructure. Understanding workflows prepares you for scaling, monitoring, and deploying AI systems in real environments. Up to this point, you have built intelligent systems, agents, workflows, structured outputs, but building is only half of engineering. The other half is evaluation. AI systems fail differently than traditional software. They degrade silently. They produce plausible errors. They shift behavior when you modify prompts or models. Day 11 is about introducing discipline into your AI systems. You will define quality criteria, create test suites, implement validation layers, and measure improvement quantitatively. This is how AI transitions from experimentation to production grade engineering. Today marks a shift from building to hardening. You've constructed AI systems that work. Now you must ensure they continue working reliably. We will focus on three pillars: measurement, regression testing, and guardrails. Measurement tells you how well the system performs. Regression testing ensures changes do not break existing behavior. Guardrails constrain outputs to acceptable boundaries. An AI system without evaluation is unpredictable. Evaluation transforms AI from creative experimentation into structured engineering. AI systems can fail without obvious errors. They often produce outputs that appear correct, but contain subtle inaccuracies or formatting inconsistencies. Small changes, adjusting temperature, updating a prompt, switching models, can shift behavior significantly. Without evaluation, you cannot detect those changes. Evaluation provides visibility. It ensures you understand when quality improves and when it degrades. In production environments, trust depends on measurable performance. AI failures are rarely catastrophic crashes. They are usually subtle deviations. Common issues include hallucinated facts, missing required fields, ignoring formatting instructions, or producing unsafe content. Sometimes the output looks polished, but violates internal policies. Recognizing these failure types allows you to design targeted tests. You cannot fix what you cannot categorize. Classification of failure modes is the first step towards systematic improvement. Quality must be defined explicitly. For structured outputs, quality might mean valid JSON with required fields. For conversational outputs, it might include clarity, tone, and relevance. For workflows, it could include policy compliance and determinism. Before testing, define measurable success criteria. Vague definitions of quality lead to vague evaluations. Precise definitions enable objective scoring. Separate what can be measured automatically from what requires human judgment. Objective evaluation includes schema validation, field presence, response length limits, and rule adherence. These can be automated reliably. Subjective evaluation includes tone quality, helpfulness, or clarity. These may require human review or LLM-based scoring. Maintaining this distinction ensures that automated testing focuses on measurable properties while leaving nuanced assessments for controlled review. Prompts are not static text, they are behavioral code. When you modify a prompt, update a model version, or adjust temperature, you change system behavior. Without regression testing, you risk breaking previously working cases. Regression testing involves running known test cases and comparing outputs to expected constraints. If behavior changes unexpectedly, you detect it immediately. A test case should include input, expected structure, and validation criteria. It should define what must be present, what must not appear, and what constitutes failure. Include representative examples and edge cases. Testing AI systems requires the same discipline as testing APIs. Inputs must be controlled, and expected behaviors must be documented. Your test suite should include diverse scenarios. Normal cases validate expected behavior. Edge cases test limits. Ambiguous cases examine instruction following. Adversarial cases test robustness. Diversity in testing improves resilience. A system tested only on ideal inputs will fail under real-world variability. Guardrails reduce unpredictability. Examples include enforcing JSON-only responses, restricting allowed output fields, setting maximum lengths, or filtering unsafe content. Guardrails are implemented outside the model through validation and filtering layers. They act as boundaries that prevent the system from drifting into unsafe or malformed outputs. Safety checks operate before and after AI execution. Pre-processing sanitizes inputs. Post-processing validates outputs. For example, you may block certain phrases, ensure required fields exist, or reject outputs that exceed length limits. Never assume the model will always behave. Verification must be external and independent. Logs provide historical insight. Each AI call should log inputs, outputs, validation status, and model parameters. Without logs, you cannot trace performance changes. Logging transforms AI behavior into observable data. Observability is essential for debugging and auditing. Metrics make quality measurable. Track JSON validity percentage, missing field frequency, average response length, error rate, and retry frequency. Quantitative metrics allow comparison across versions. Metrics transform subjective impressions into engineering evidence. In this lab, you will take an existing AI system and harden it. You will create a test suite, automate validation, implement guardrails, and measure improvements. This is iterative engineering. Define representative test cases as structured data. Each case should include input text and validation rules. Store them in JSON or YAML format for repeatability. A test suite is your safety net for future changes. Your evaluation script should loop through test cases, call the AI system, validate responses, and record pass-fail status. Automated evaluation removes subjectivity and ensures consistency across runs. Schema validation ensures outputs follow strict structural rules. define required fields, allowed values, and type constraints. Reject outputs that fail validation. Schema enforcement dramatically reduces structural errors. Safety filters scan outputs for disallowed patterns or policy violations. This may include checking for restricted phrases or excessive length. Safety filters add an additional protective layer. When failures appear, refine prompts strategically, clarify instructions, add examples, reduce ambiguity, and retest. Improvement must be iterative and measured. Compare metrics before and after changes. Track failure reduction and compliance improvement. Quantitative comparison proves effectiveness. You should now have an evaluated and hardened AI system. It includes a test suite, automated validation, guardrails, logging, and measurable metrics. This transforms AI experimentation into engineering discipline. Trust enables scale. Without evaluation, AI remains a prototype. With testing, guardrails, and metrics, it becomes production-ready infrastructure. Day 11 marks your transition from AI builder to AI engineer.
Welcome to week 8, Model Tuning and Optimization. Our week will start with day 1 introducing to hyperparameter tuning. Day 2, we will look at grid search and random search. Day 3, we look at some advanced hyperparameter tuning with Bayesian optimization. Day 4, we'll be looking at regularization techniques for model optimization. Day 5, we'll be looking at cross-validation and model evaluation techniques. Day 6 will be about automated hyperparameter tuning with grid search CV and randomized search CV. And finally, day 7 will be our optimization project where we will be building and tuning a final model. So let's get started with week 8.
Until now, everything you built has lived locally. It worked on your machine. It passed your tests. But real impact begins when your system is accessible to others. Day 12 is about operationalizing your work. Deployment is not just pushing code to a server. It is about security, environment configuration, reliability, and exposure to real users. You will learn how to prepare your application for production, manage secrets safely, deploy to the cloud, and share a public URL. This is the transition from project to product. Today marks a major milestone. You are moving from local development to public availability. So far, you've built agents, workflows, and evaluated systems. Now, you will make them accessible via the internet. This requires careful preparation, securing secrets, defining environment variables, and ensuring your application can start cleanly in a cloud environment. Deployment transforms experimentation into distribution. By the end of today, your AI system should be reachable via a live URL. An application that runs only on localhost is not scalable. Real users cannot access it. Stakeholders cannot test it. Feedback is limited. Deployment enables accessibility and validation in real-world conditions. It introduces constraints such as network latency, cloud resource limits, and public security risks. These constraints are not obstacles. They are part of production engineering. If your system cannot run reliably in a live environment, it is not yet ready for real impact. There are several hosting models available. Platform as a service platforms abstract away server management and make deployment simple. Virtual private servers provide more control, but require more configuration. Serverless platforms scale automatically, but may impose execution limits. Choosing the right model depends on your needs. For this lab, simplicity is key. A managed platform allows you to focus on deployment fundamentals rather than infrastructure management. Understanding these models prepares you for more advanced scaling decisions later. Platform as a service simplifies deployment. You connect a repository, configure environment variables, and the platform builds and runs your app automatically. A virtual private server gives you full control, but requires manual server setup, networking configuration, and maintenance. It introduces operational overhead. For most early stage AI apps, PaaS is sufficient. The goal is to deploy reliably and securely without unnecessary infrastructure complexity. Before deployment, clean your project. Remove debug statements. Confirm dependency lists are accurate and ensure error handling is in place. Most importantly, remove all hard coded secrets. API keys and tokens must never be committed to source control. Deployment amplifies small mistakes. A misconfigured dependency or missing environment variable will cause failures in the cloud. Preparation prevents unnecessary debugging later. Environment variables allow you to configure secrets and runtime settings without embedding them in code. Locally, you may use a .env file. In the cloud, you configure environment variables in the platform dashboard. Your application reads them at runtime. This separation ensures secrets remain secure and can be changed without modifying source code. It also enables different configurations for development and production environments. Security must be considered from the start. Validate inputs to prevent abuse. Limit request sizes. Avoid exposing sensitive system information in error messages. Ensure your AI API key is used only on the back end. Never send it to the front end. Implement minimal rate limiting to avoid abuse or runaway costs. Basic security practices significantly reduce risk. Your deployed app should run over HTTPS. Most managed platforms provide SSL certificates automatically. Encryption protects data in transit between user and server. Additionally, all AI API calls must originate from your backend, not directly from the browser. This prevents secret exposure. Secure transport and backend isolation form the foundation of safe AI deployment. In production, the browser communicates with your cloud-hosted backend. The backend processes the request, calls the AI API securely, and returns the result. This layered architecture protects secrets and centralizes control. The backend acts as a security boundary between public users and external AI services. Understanding this flow clarifies where validation, logging, and monitoring should occur. In today's lab, you will deploy your web-based AI application to a cloud platform. You will connect your GitHub repository, configure build and start commands, set environment variables, and monitor logs during deployment. Finally, you will test the public URL and verify behavior. The goal is not just to deploy successfully, but to deploy responsibly. Review your repository carefully. Confirm that requirements.txt lists all dependencies. Ensure there are no hard-coded API keys. Verify that your application starts locally using the same command the cloud will use. Professional deployment begins with repository discipline. Modify your application to read secrets from environment variables. For example, retrieve the AI API key using os.getev. Ensure your application handles missing variables gracefully by raising a clear error rather than crashing silently. Configuration management separates secure runtime data from source code. Cloud platforms require a clear start command. Whether you use Uvicorn, Gunicorn, or Python app.py, the command must launch your application reliably. Test this command locally before deploying. If it fails locally, it will fail in the cloud. Clarity and startup configuration reduces deployment friction. Select a hosting provider that supports your stack. Managed platforms simplify this process by handling build and runtime configuration automatically. The goal is to minimize infrastructure complexity and focus on application behavior. Choose reliability over novelty. Push your code to GitHub. Connect the repository to your hosting platform. Configure the build and start commands. Most platforms will automatically rebuild and redeploy on each push. This enables continuous deployment and rapid iteration. Automation reduces operational overhead. In the platform dashboard, add your API keys as environment variables. Do not commit them. After adding variables, redeploy your app so the new configuration takes effect. Environment configuration is a critical deployment step. Trigger deployment and watch build logs carefully. Check for dependency errors, missing modules, or startup failures. Logs are your primary debugging tool in production. Learn to read them carefully. Monitoring is part of deployment discipline. Once deployed, test the application thoroughly. Verify correct responses, input validation, and structured outputs. Test edge cases and error states. Production behavior may differ from local behavior due to environment differences. Validation confirms successful deployment. Public applications are exposed to abuse and excessive usage. Implement simple rate limiting or request throttling. This protects your AI API budget and reduces risk of denial of service behavior. Basic protective measures prevent unnecessary operational issues. Once stable, share the public URL. Gather feedback, monitor logs, track usage patterns. Deployment is not the end of development. It is the start of real-world iteration. Users will reveal edge cases you did not anticipate. By the end of day 12, you should have a live AI application accessible via a public URL. It should be securely configured, validated, and monitored. Your application has moved from local experimentation to distributed availability. This marks your transition from developer to deployer, from building AI systems to shipping them. Up to this point, your AI system has lived in a controlled environment, your laptop. It worked locally, passed your evaluations, and behaved as expected. But real systems must operate beyond your machine. Today's lab is about operationalizing your work. Deployment introduces new variables: environment configuration, security boundaries, logging, and real-world traffic. You will prepare your application for production, deploy it to a managed cloud platform, configure secrets securely, validate behavior in a live environment, and share a public URL. This is the transition from building AI to shipping AI. Today's objective is to deploy your AI application to the cloud and make it publicly accessible. This involves more than clicking a deploy button. You must prepare your codebase, configure secure environment variables, define a proper start command, and verify that your application runs correctly in a remote environment. By the end of this lab, your system should be accessible via a live URL and capable of handling real user requests. This is the moment your project becomes a deployable product. Before deploying, understand the architecture. A user sends a request from their browser to your cloud-hosted backend. The backend processes the request and securely calls the AI API. The response flows back through the backend to the user. The backend acts as a security boundary. It protects your API keys and enforces validation and logging. The front end should never hold secrets. Understanding this flow ensures you deploy responsibly and securely. Deployment begins with discipline. Remove debug print statements. Confirm that all dependencies are listed in requirements.txt. Ensure .env is excluded via .gitignore. Search your repository for any hard-coded API keys or tokens. They must not exist in committed code. Production environments expose your code publicly, and secrets must never travel with it. A clean repository reduces deployment failures and prevents security risks. Secrets must be externalized from your code. Instead of hard-coding your AI API key, retrieve it using environment variables such as os.getM. Cloud platforms provide dashboards where you can securely inject environment variables at runtime. This keeps your credentials private and changeable without modifying code. If your application cannot start without a key, ensure it fails clearly and logs an informative message. Cloud platforms require a clear command to start your application. For example, with Fast API, you might use Uvicorn main.app host 0.0.0.0 -port $port. Test this command locally before deployment. If it fails locally, it will fail remotely. This simple verification prevents avoidable cloud debugging. Clear startup configuration is essential for reliable deployment. Most managed platforms deploy directly from GitHub. Push your cleaned repository to your remote branch. Version control enables reproducibility. If deployment fails, you can track exactly what changed. Continuous deployment platforms rebuild your app automatically when you push updates. Deployment workflows depend on source control discipline. Select a managed platform that supports your stack. Platforms like Render or Railway simplify Python deployment. The goal is not to master infrastructure management, but to understand deployment fundamentals. Choose reliability and clarity over complexity. Managed platforms allow you to focus on application behavior instead of server configuration. Within your chosen platform, create a new web service and connect your GitHub repository. Select the correct branch. The platform will automatically build your project using the commands you provide. This process transforms your repository into a running application. This step connects development and production. Define how your application is built and started. The build command typically installs dependencies. The start command launches your server. These commands must be accurate and tested locally. Incorrect commands are a common cause of deployment failure. Clarity here ensures smooth builds. In the platform dashboard, add your API key as an environment variable. Do not expose it publicly. After adding variables, redeploy your app so the new configuration is applied. Without proper environment configuration, your app may start but fail when calling the AI API. Secret management is central to secure deployment. Initiate deployment and monitor logs carefully. Logs will show dependency installation and application startup messages. If errors occur, read logs methodically. Fix issues locally, commit changes, and redeploy. Cloud debugging requires patience and precision. Logs are your window into production behavior. Once deployed, the platform provides a public URL. Open it and test functionality thoroughly. Verify correct responses, structured outputs, and error handling. Confirm that invalid inputs are handled safely. Production environments sometimes behave differently than local ones. Validation is essential. Public systems encounter unpredictable inputs. Test empty requests, malformed JSON, long inputs, and rapid repeated calls. Observe how your system behaves under stress. Production testing should simulate realistic and adversarial scenarios. Robust systems anticipate edge cases. Consider implementing simple rate limiting or request throttling. Public endpoints are susceptible to abuse or accidental overuse. Basic protections help control API costs and prevent denial of service patterns. Even simple safeguards dramatically improve stability. Security and cost management are part of responsible deployment. Once your application is stable, share the public URL. Encourage feedback and monitor logs. Deployment is not the end of development. Real-world usage reveals insights you cannot simulate locally. Continuous iteration is part of production life. Sharing your application validates your entire 12-day journey. Expect common issues such as missing environment variables, incorrect module paths, or incomplete dependency lists. Most deployment errors are configuration mistakes rather than code failures. Approach debugging systematically. Read logs, isolate the issue, fix locally, and redeploy. Deployment discipline grows with experience. By the end of this lab, you should have a live AI application accessible through a public URL. It should be securely configured, validated, and stable under real use. You have moved from local experimentation to distributed deployment. This is where AI development becomes AI delivery. For the past 12 days, you've built components, APIs, prompts, structured outputs, memory systems, agents, workflows, deployment pipelines, evaluation layers. Today is different. Today is about integration. Real AI systems are not isolated scripts. They are cohesive products made of multiple moving parts that work together reliably. The capstone build day is where you combine UI, AI logic, memory, tools, automation, evaluation, and deployment into one unified system. This is where you stop being someone who builds AI features and become someone who builds AI products. Today is integration day. Everything you've built so far has been modular, individual capabilities designed to teach specific concepts. But real world systems require orchestration. You will combine front end interfaces, back end AI logic, memory layers, tool execution, structured validation, and automation into a cohesive application. The goal is not to experiment. The goal is to produce a complete, working AI product. This is the moment where your technical skills must align with product thinking. A product is not a model call. It is not a prompt. It is not a clever workflow. A product solves a real problem for a defined user through a reliable, usable system. It includes user interface design, back-end orchestration, memory handling, error management, and predictable outputs. The difference between a demo and a product is intentional integration. Your objective is to build one cohesive AI system. It must include a user interface, AI reasoning, persistent memory or state, at least one functional tool, and a basic automation component. These parts must interact cleanly. The system should feel intentional, not stitched together. Integration clarity determines quality. Choose a meaningful use case. Productivity assistant, research agent, internal workflow tool, document analyzer. Choose something you understand. A vague product leads to vague implementation. A clear use case defines architecture, features, and constraints. Clarity in problem selection simplifies integration decisions. Every system serves someone. Define who that person is. What is their workflow? What friction are they experiencing? What outcome do they expect? Your architecture must reflect user reality. Products succeed when they align tightly with user context. Scope discipline is critical. Your product must include input, reasoning, memory, a tool, structured output, and basic validation. Do not attempt excessive features. A focused minimum viable product integrates cleanly. Overscoping creates brittle systems. Before coding, draw the architecture. Map the flow from user input to back-end logic, to memory retrieval, to tool execution, to validated output. Clarity at the architecture level prevents integration chaos. The back-end orchestrates everything. It receives input, retrieves context, calls the model, executes tools, validates outputs, logs activity, and returns results. This orchestration layer must remain clean and modular. Back-end discipline determines system stability. Memory transforms a stateless system into a contextual one. Implement session tracking or persistent storage. Manage context windows carefully. Avoid unbounded memory growth. Memory design influences system intelligence. Tools allow your AI to act. Whether writing files, querying documents, performing calculations, or triggering workflows, tools extend the system beyond conversation. Tool invocation must be controlled and validated. Automation moves your system beyond reactive responses. Implement event triggers or multi step chaining. Even a simple workflow adds depth. Automation demonstrates systems thinking. Start with a stable backend endpoint. Enforce structured inputs and outputs. Integrate your validation layer. The backend must function reliably before UI polish. Stability first. The UI must clearly communicate input, processing state, and output. Handle loading states. Display errors cleanly. Preserve formatting. User experience reflects system maturity. Integrate memory carefully. Persist relevant context. Prune irrelevant data. Memory should enhance reasoning, not clutter it. Context management defines system intelligence. Integrate at least one tool meaningfully. Ensure invocation conditions are clear. Validate tool outputs before returning them. Tools convert intelligence into action. Activate validation from day 11. Reject malformed outputs. Enforce schema. Apply safety filters. Integration without guardrails is risky. Run complete workflows. Test normal inputs, edge cases, repeated sessions, and tool failures. Integration failures often appear at system boundaries. Test thoroughly. Improve clarity. Reduce latency. Simplify messaging. Professional systems feel intentional. Refinement differentiates good from excellent. Push updates. Redeploy. Verify behavior in production. Real world environments expose integration weaknesses. Deployment is part of integration validation. Your deliverable includes product name, defined use case, architecture explanation, working demo, and repository link. Integration is mastery. You've moved from isolated experiments to a unified AI system. This is what separates AI hobbyists from AI product engineers. For 12 days, you've built components, APIs, memory systems, agents, workflows, guardrails, deployment pipelines. Today, you stop building parts and start building a product. Capstone Day is about integration. Real AI systems are not isolated scripts, they are coordinated systems where UI, backend logic, memory, tools, automation, and validation all work together. Your goal today is not experimentation, it is execution. By the end of this lab, you should have a cohesive AI product that solves a real problem for a defined user and demonstrates your ability to integrate everything you've learned. Today's objective is simple but ambitious. Build a complete AI product. This is not about writing more prompts. It's about orchestrating everything: UI, AI reasoning, memory, tools, automation, validation, and logging into one working system. Integration is the skill that separates feature builders from product engineers. By the end of this lab, your system should function end to end without manual intervention between steps. It should feel intentional, not stitched together. Think in terms of systems, not scripts. Your first decision determines everything else. Choose a specific product type, not a generic chatbot, not a vague assistant. Pick a focused system: a meeting summarizer, a support triage tool, a productivity planner, a research assistant, or a document analysis tool. The narrower the problem, the stronger your architecture decisions will be. Clarity of scope simplifies integration. Broad ambitions create fragile systems. Define who your product serves. What is their role? What is their daily workflow? What friction are they experiencing? You must articulate the problem clearly before writing more code. Your backend decisions, memory design, and automation flow should reflect real user behavior. A well defined user prevents over engineering and keeps your product grounded in real value. Scope discipline is essential. Your minimum viable product must include a UI, AI reasoning, memory, at least one tool, automation, and validation guardrails. Anything beyond that is optional. If you attempt to build too much, integration will break. Focus on a coherent core. A well integrated small system is more impressive than a half finished ambitious one. Before coding further, draw the system flow. Map user input through the UI to the backend, from backend to memory, from memory to AI, from AI to tool invocation, through validation, back to the user. Architecture clarity prevents chaos during integration. When systems fail, it's often because relationships between components were never defined clearly. Design first, then build. Every boundary needs a contract. Define what your UI sends to the backend. Define what your backend returns. Define how memory is structured. Define how tools accept and return data. Without explicit schemas, integration becomes guesswork. Clear contracts turn integration into structured engineering. Your backend is the orchestration layer. It must expose clean endpoints and coordinate AI calls, memory retrieval, tool execution, and validation. Keep it modular. Separate logic into functions. Avoid mixing UI logic with AI logic. A stable backend is the foundation of your capstone. Start with the simplest reliable AI call. Ensure your system prompt is precise. Use structured output when possible. Test this independently before layering on memory or tools. If your core reasoning is unstable, integration will amplify problems. Build a reliable core before expanding. Now introduce persistence. Each session should store relevant conversation history or extracted state. Choose a simple storage method, JSON files or SQLite. Avoid complexity unless necessary. Memory should enhance reasoning, not create unpredictability. Manage context windows carefully. Memory must actively influence reasoning. Before calling the model, retrieve prior context and inject it into the message structure. Limit history to prevent uncontrolled growth. Test follow up questions to confirm memory works correctly. Multi turn coherence is the mark of stateful intelligence. Your product must act, not just respond. Implement one deterministic tool. It might write a file, search documents, extract structured data, or generate a task plan. Tools should have clear interfaces and predictable outputs. They must not rely on model guesswork. Integrate the tool meaningfully. Trigger it through explicit logic or within a workflow. Ensure tool outputs are validated before returning them to the user. A tool that runs but is not integrated into user experience is incomplete. Action is what differentiates AI systems from chat interfaces. Automation is about chaining logic. Build a workflow runner that sequences steps: extraction, validation, generation, artifact creation, logging. Encapsulate this in a single function or endpoint. Ensure each step passes structured outputs to the next. Workflow discipline ensures reliability. Your workflow must be triggered intentionally. This could be a UI button, a scheduled job, or a specific API call. Triggers make automation tangible. The system should run end to end without manual intervention between steps. This demonstrates system level thinking. Reapply your day 11 lessons. Validate JSON outputs. Enforce required keys. Apply safety checks. Implement bounded retry logic. Guardrails are non negotiable. Integration without validation leads to silent failure. Logging creates visibility. Record session IDs, tool usage, validation results, and errors. Logs enable debugging and demonstrate production awareness. A system without logging is opaque. Build a simple but functional interface. It must accept input, show output clearly, display loading states, and handle errors. The UI translates system complexity into user clarity. Test the full chain: UI, backend, memory, AI, tool, validation, UI. This is the true integration moment. Ensure each boundary passes structured, predictable data. Rerun your automated test suite. Ensure integration has not broken output guarantees. Regression testing protects system integrity during integration. Simulate real user behavior. Test edge cases, tool failures, and multi-turn memory. Integration failures often emerge at boundaries. Test thoroughly. Your final product must include documentation, architecture overview, working system, and optionally a deployed URL. This is your portfolio artifact. It demonstrates integration mastery, not just AI familiarity. For 13 days, you've built real AI systems. You designed architectures, integrated memory, implemented tools, automated workflows, added validation, and deployed applications. But building is only half the journey. Day 14 is about leverage. Your work creates opportunity only when it is visible, understandable, and positioned correctly. Documentation, demos, and portfolio presentation determine whether your projects open doors or remain private experiments. Today, you will package your capstone into a professional artifact that communicates engineering maturity, systems thinking, and production readiness. This is how you turn code into credibility. Today is about transformation, not of your code, but of your positioning. You've built a complete AI product. Now you must document it, present it, and package it in a way that signals competence to employers, clients, or collaborators. Technical ability is necessary, but visibility and clarity are what create opportunity. By the end of today, you should have a polished GitHub repository, a professional README, a demo recording, and a portfolio-ready summary that clearly communicates the value of your project. Most developers stop after writing code. That is where many opportunities are lost. Decision makers rarely read source code first. They read your README, they watch your demo, they scan your architecture explanation. Clear documentation reduces friction and increases trust. Well-structured documentation signals organization, communication skill, and engineering maturity. It tells the reader that you understand not just how to build, but how to explain. A portfolio-ready AI project is not just functional, it is intentional. It clearly defines the problem it solves. It explains the target user. It includes an architecture diagram, setup instructions, screenshots, and optionally, a live URL. It demonstrates integration, UI, memory, tools, validation, and deployment. And it communicates these elements concisely. Professional presentation turns a technical artifact into a compelling case study. Your README is the front page of your project. It should start with a concise description: what the project is and what problem it solves. Then explain features, architecture, and setup instructions. Avoid clutter. Structure the document logically. Use headings. Keep language clear and professional. A strong README allows someone unfamiliar with your project to understand its purpose and value within minutes. Structure communicates thinking. Begin with an overview, then describe the problem and motivation. Include your architecture diagram and technical stack. List features clearly. Provide setup instructions and example usage. Conclude with deployment details and future improvements. A structured README reflects structured engineering. Architecture diagrams communicate systems thinking. Even a simple flow diagram, user, UI, backend, memory, tools, AI, validation, output, demonstrates understanding of integration boundaries. This tells readers you are not merely calling an API, but designing a cohesive system. It distinguishes you from prompt level builders. Architecture explanation is a strong credibility signal. Include a section explaining why you made certain decisions. Why did you choose file-based memory over a database? Why structured outputs? Why implement validation guardrails? What trade-offs did you consider? Explaining trade-offs demonstrates maturity. It shows you understand engineering constraints and not just implementation steps. Design rationale elevates your project from technical artifact to engineering case study. A short demo amplifies clarity. Begin by stating the problem, then briefly explain the architecture. Show live interaction with your system. Demonstrate tool usage or automation. If deployed, show the public URL. Keep it concise and focused. 5 minutes is ideal. A clear demo builds confidence and makes your project tangible. Structure your demo like a story. First, describe the problem. Second, introduce your solution. Third, explain architecture at a high level. Fourth, demonstrate functionality. Finally, mention next improvements. This narrative flow keeps viewers engaged and communicates professionalism. Clarity in storytelling reflects clarity in thinking. Remove unused files. Ensure folder organization is clean. Add a .env example file instead of exposing real keys. Confirm dependencies are accurate. Your repository should feel intentional and structured, not experimental. Comments should clarify important logic, not restate obvious code. Polish reflects discipline. Craft a concise resume-ready description. Focus on impact and integration. Mention architecture, AI logic, memory persistence, tool execution, deployment, and validation guardrails. Avoid vague phrases like worked on AI. Be specific. Quantify when possible. This summary becomes part of your professional narrative. Translate your project into enterprise-relevant capabilities. Highlight system architecture, API integration, agent design, deployment, evaluation frameworks, and automation workflows. Frame your work in terms that organizations understand: reliability, scalability, security, integration. Positioning transforms a project into proof of competence. Visibility multiplies impact. Share your project on LinkedIn with a clear summary and demo link. Publish a GitHub release. Consider writing a short technical blog post explaining what you built. Visibility creates surface area for opportunity. Explain your project publicly. Describe the problem, your architectural approach, integration challenges, and lessons learned. Mention trade-offs and improvements you would make. Teaching reinforces expertise and demonstrates communication ability. A well-written technical post strengthens your professional brand. Be prepared to discuss your design decisions. Explain why you structured memory the way you did, how you validated outputs, how you handled prompt injection risks, how you deployed securely. Depth matters more than buzzwords. Your capstone should allow you to speak confidently about real engineering trade-offs. Preparation turns projects into interview advantage. Day 14 is not the end. Refactor for scalability. Add monitoring, Improve UI, enhance tool planning logic, extend automation. Professional growth is iterative. Continue building and improving. Your final deliverable is a portfolio ready AI project with a clean repository, structured README, architecture diagram, demo recording, and optional live deployment. This is your leverage asset, a visible demonstration of your capability to design, integrate, and ship AI systems. You began with foundational concepts. You now understand architecture, memory, agents, workflows, deployment, evaluation, and professional documentation. You have moved from experimentation to integration to positioning. That progression is what defines an AI product engineer. For 13 days, you focused on building. Today, you focus on leverage. Your AI product is only as powerful as your ability to communicate it. Employers, clients, and collaborators do not see your thought process. They see your repository, your documentation, and your demo. Day 14 is about transforming your capstone into a professional artifact that signals clarity, structure, and engineering maturity. You will write strong documentation, record a focused demo, and polish your repository so that it reflects intention rather than experimentation. This is where technical work becomes career capital. Today's objective is to package your AI product professionally. You will create structured documentation, record a clear demo, and refine your repository to production level standards. This is not cosmetic work, it is strategic work. Documentation clarifies your thinking. A demo proves your system works. A clean repository signals discipline. By the end of this lab, your project should feel intentional, complete, and presentation ready. This is how you move from student project to portfolio asset. Organization is the first signal of professionalism. Create a dedicated docs folder. Separate architecture documentation, design decisions, and demo scripts from your code. Structure tells reviewers that you think systematically. When documentation is scattered or missing, it suggests experimentation. When documentation is structured, it suggests engineering discipline. Keep your project clean and navigable. Your README is your project's landing page. It must communicate value quickly. Start with a concise description. Define the problem clearly. Explain what your solution does. Then describe features and architecture at a high level. Avoid vague language. Avoid long paragraphs. Use headings and bullet points. Clarity and brevity demonstrate confidence. If someone reads only your README, they should understand what your system does and why it matters. Structure your README logically. Begin with overview and motivation, then architecture, then technical stack, then setup instructions, then deployment. End with future improvements. This structure mirrors how engineers think: problem, design, implementation, operations. A well structured README communicates that you approach systems methodically. An architecture diagram elevates your project. Even a simple flow diagram demonstrates that you understand system boundaries. Show how UI connects to backend, how memory integrates, how tools execute, how validation protects outputs. Architecture diagrams communicate systems thinking. They show that you built an integrated solution, not a collection of prompts. This is one of the strongest signals of engineering maturity. Great engineers explain trade offs. Why did you choose file based memory instead of a database? Why structured JSON outputs? Why enforce validation guardrails? Create a design decisions document that answers these questions. Explain constraints and reasoning. This shows depth of understanding. It demonstrates that you can justify architectural choices, not just implement them. Security is part of professionalism. Provide a .mv example file with placeholder values. Clearly explain required environment variables. Confirm that secrets are excluded from version control. This communicates that you understand production discipline and secure configuration. Even small security details reflect maturity. Before recording, write a script. Outline the problem. Introduce the solution. Briefly describe architecture. Demonstrate features in a structured order. Show tools and automation. End with deployment proof. Planning your demo prevents rambling and ensures clarity. A concise narrative is more persuasive than a long, unstructured walkthrough. Keep your demo between 3 and 5 minutes. Show the application running. Demonstrate multi-turn memory. Trigger a tool. Execute an automation workflow. Optionally, show validation behavior. Speak clearly. Focus on clarity over complexity. This demo should show confidence and understanding, not improvisation. A strong demo builds trust. Upload your demo to a reliable platform. Make it accessible but professional. Add the link prominently in your README. Visibility increases opportunity. Without sharing, your work remains hidden. Your demo is the bridge between technical implementation and external recognition. Now refine your repository. Remove unused files. Delete experiments. Organize folders clearly. Ensure naming is consistent. A clean repository reflects intentional engineering. Clutter suggests unfinished thought. Imagine a hiring manager browsing your repository. Make their experience frictionless. Your README should contain clear, copy-paste commands to run the project locally. Test your instructions from scratch. If they fail, fix them. Simplicity matters. Ease of setup demonstrates consideration for users and collaborators. A project that cannot be run easily loses credibility. Visual elements increase clarity. Add UI screenshots, workflow outputs, and example results. Screenshots make your project feel tangible. They also help non-technical reviewers quickly understand what you built. Visual proof strengthens documentation. Conduct a final audit. Search for committed secrets. Confirm dependencies are correct. Ensure logs and temporary files are excluded. Verify the documentation matches implementation. This step reinforces discipline. Attention to detail matters in professional environments. Make a final, intentional commit. Use a clear message describing the polish and documentation updates. Push to GitHub. Review the repository in a browser as if you are a third party. Presentation matters. At the end of this lab, you should have a clean, structured GitHub repository, a professional README, architecture and design documentation, a concise demo video, and a deployment link if available. This is your portfolio-ready AI project. It represents not just what you built, but how you think and communicate as an engineer.